A confirmation about the audio, please, guys, if the audio is clear and available. Thank you. So before the break, we had been discussing about the unicellular model of circulation as postulated by Hadley. Now, that unicellular model of circulation by Hadley had got certain drawbacks due to which it was eventually rejected. Now, what were the drawbacks? The drawbacks were very simple and straightforward in the sense that Hadley had said that look, you only have the existence of the thermal pressure zones or the pressure zones induced due to the thermal conditions, and you have basically heating at the region of equator and very cold conditions at the region of the poles. They are driving the pressure differences and they are driving the movement of air. So what Hadley said was basically at the region of equator, as it gets heated up, air rises up significantly. Okay, then it diverges at the region of the tropopause. It reaches the region of the poles, where due to very cold conditions you have a sinking air column, you have a very high pressure, and that induces a circulation. And this was the unicellular model of circulation. But in the 1800s, you had an American climatologist with the name of William Ferrel. Now, William Ferrel basically came upon the conclusion that look, you cannot have an upper air movement all the way from the region of equator to the region of the poles, because that is what Hadley had said, that in the upper air the air is moving from the region of equator to the poles. And Ferrel basically held the opinion that look, it cannot be possible because the Coriolis force will induce a bending, so it will never be able to reach the poles. And also on the ground surface, due to the presence of the friction force, you can never have an air parcel which has originated around the region of the poles and has extended all the way to the region of the equator. That cannot be a reality. So that is when, after many different levels of understandings and also the researchers and the various different observations made by the sailors, the mariners of that point of time, a global air circulation model was arrived at. And this was what was referred to as the tricellular model of atmospheric circulation. Okay, this was your tricellular model of circulation. Now, what was this? So here, what we will do is, we will basically be analyzing this tricellular model on the ground surface with only one hemisphere is what we will consider. We'll try to consider only the northern hemisphere for easier understanding. And the same thing and the same process will also be replicated in the southern hemisphere. Okay. Here, we will basically be also considering this planet or the model of it to indicate to you what is the upper air movement, that is in the upper region of troposphere. Upper air movement. Okay. Now, let us understand how is it that this circulation takes place. So basically, let us assume this is your 0 degree, that is equator, 30 degree, 60 degree, and 90 degree. Okay. You might have 30 degrees south here as well. I am taking 30 degree as an average. Please don't think about it that this cannot happen at 29 degree. This will happen only at 30 degree. Okay, please don't think about it that it cannot happen at 60 degree. Or rather, let's do one thing. Let's have an approximation here so that it is less confusing for you guys as well. So let's think about it, 25 degree to 30 degree. Now, here, what happens at the region of equator, around equator? Basically, that is the region which experiences very high amount of solar insolation. On an average throughout the year, that is a region of heat surplus. So due to that high amount of solar insolation, the air in that area, obviously the ground will get heated up. Once the ground gets heated up, then basically it will heat up the air also above the ground. Now, when the air above the ground is heated up, the air will start to rise. Pay attention here very carefully, because if you understand this tricellular model of circulation, then your understanding of jet streams, El Nino, Indian Ocean dipole, Indian monsoon, all of those understandings become much easier. Even for that matter, cyclonic circulations, the movement of them, everything becomes much easier. Okay. So here at the region of equator, you have the warming of the ground, due to which the air starts to rise up. Now, as the air tends to rise up, basically, it will rise up till what? Generally, up till the level of tropopause. Up till the level of tropopause is where the air will rise up. Now, after hitting the tropopause, it will diverge. One portion will go into the southern hemisphere, other portion will go into the region of the northern hemisphere. Now, here we have used this, or we have basically put it up to have an understanding of what happens in the upper air, this particular region, how does it behave. Now here, if I talk about upper air wind movement, which is moving from the region of equator, one of that is moving towards the region of southern hemisphere, other is moving towards the region of northern hemisphere. So it will experience Coriolis force. So here, let's suppose in the upper air, from equator, the wind is moving. It will get diverted in the rightward direction due to Coriolis force, isn't it? Due to Coriolis force. Now, here, what do you observe in this region, in this entirety of the area? The air starts accumulating. The wind and the air here starts to accumulate. Why is it the case? Because of the Coriolis force bending, or the influence of the Coriolis force, these upper air wind, they will never be able to reach the poles. There will be so much amount of deviation and diversion, they will never be able to reach the poles. So they will start accumulating here. Somewhere in the region of 25 to 35-degree north latitude, they will start to accumulate. And meanwhile, more air is rising up from the region of equator. Much more air is rising up from the region of equator, because the region of equator is getting heated up. Meanwhile, the air which has accumulated in this portion around the tropics in the upper atmosphere, that would also start becoming colder, because it is in the region of tropopause now. Temperature close to around -60, -70 degrees Celsius. So not only do you have an immense accumulation of air, you also have that air getting colder. So as a consequence, the air starts to sink. Here, when there is a lot of accumulation in this area, eventually this is the region where there is so much amount of accumulation of that upper air. That is where the air actually begins to sink. It sinks. And after sinking, it hits the ground. Upon hitting the ground, this will diverge, right? One portion will go towards the region of equator to fill the vacancy created at the region of equator. Okay. Other portion will go towards the region of the poles. Okay. Meanwhile, what is it that is happening at the polar area? In the poles, it is very, very cold. Throughout the year, the temperature is very low. So you have an absolute thermal high pressure created because of very cold conditions. So here, due to very cold conditions, you have a thermal high pressure at 90 degrees. So you have the sinking air, and that sinking air diverges, hits the ground, and it moves. Here also air is coming from the region of the tropics. Now, both this air movement or wind movement, both of them, they will converge at the region around 60 degree. That is where the actual convergence takes place. Now, as they will converge, they will have no other place to go but to rise up. They will rise up. Right? We have seen earlier in the case of the dynamic pressure zones that when there is convergence, there is no other place to go but then to rise up. So they will start to rise up. And they will rise up to what level? Up till the level of tropopause, isn't it? So there again, they will diverge. They will be diverging here. Isn't it? One portion here will go to the region of the subtropics. It will again lead to the accumulation of air which was already happening in this region in the upper air, and that will again sink. Right? So this completes a kind of an air circulation in each hemisphere. You will have almost a similar pattern when you observe it in the southern hemisphere also. You will come across a kind of a similar pattern here also. Okay. So in each hemisphere, you have three of the cells which are created, cells of circulation. And that is why this is what is referred to as the tricellular model. Tri means three. So that is why tricellular model of circulation. That is, you have three cells of circulation in each one of them. Now here, if you analyze these cells again individually, here at the region around 0 degree, you will find that there is a low pressure. And that low pressure is created because of heating. So this is a thermal low pressure. This is also what is referred to as equatorial low. Equatorial low. Then at the region of the poles, you have high pressure, but that again is a thermal high pressure because of very, very cold conditions at the region of the poles. So this is also what is referred to as polar high. So basically, you have these two thermal pressure zones in existence, equatorial low and polar high. Now, these are driving the winds from the poles and the equator. But then in between them, you have another cell of circulation, which is purely induced due to the dynamic movement of the wind. So, for example, in this area, that is around 25 to 30 degree. In fact, in the real terms, it is almost around 30 degrees. So basically, at 30 degree north, we are talking about the region which is still in the subtropics, right? So at 30 degree north, you will find that temperature is higher. It is warmer, but still there is a high pressure. Why? Because you have a sinking air column. You have the air column which starts to sink to the bottom. So here again, you have a sinking air column. So this ends up creating a high pressure. But this high pressure is a dynamic high pressure. Okay, because had it not been the sinking of air in this region would have been warmed up, so it would have risen up as well. So here you have a dynamic high pressure, that is subtropical high. Okay, that is what is a subtropical high. Then again, the winds from the subtropical high, one of them goes to the region of equator to fulfill the vacancy created due to the rising of air. One of them comes towards the region of the poles but cannot reach the poles before itself. You have these winds from the tropics encountering the polar winds. And then when there is a convergence at around 60 degree north, these winds will start to rise up. And as they start to rise up on the ground, they will create that low pressure. But this low pressure is again not thermally induced. This low pressure is purely impacted because of the convergence of the winds and their rise up. So think about it. Had this region ideally 60-degree north, that is the northern portion of Europe or the central northern portion in general, that would be colder. Ideally, that should have the presence of a kind of a high pressure. But here you have a low pressure. Why? Because of the dynamic movement of the wind. So here you have what is referred to as the subpolar low. Subpolar low. And this low pressure is again induced due to what? Induced due to the dynamic factor or a dynamic pressure zone. So accordingly, you have three unique cells of circulation which are created, and these are named as the Hadley cell, the Ferrel cell, and the polar cell. Okay, so these three cells are present in each of the hemisphere, in both the hemispheres, hence the tricellular model. Now, here, if we talk about the region around 0 degree, it is not always going to be the case that pinpointedly at 0 degree only you will have the absolute high temperature where the air will start to rise up. That will not always be the case. It can sometimes happen at 5 degrees, sometimes can happen at 10 degrees, sometimes can happen at 7 degree, and so on. But here, what do you observe? You will observe that in that region at equatorial low, you have winds coming from tropics from both the hemisphere. From the northern hemisphere also winds are coming from the tropical area. From the southern hemisphere also winds are coming from the tropical area. So this is a zone for convergence of tropical winds, isn't it? Tropical winds from both the northern and the southern hemisphere, they are converging at this region of 0 degree or equatorial low. So that is why this is what is also referred to as intertropical convergence zone, or ITCZ. Convergence zone. That is ITCZ. Okay? This is your region where winds from both the tropics, they come in to fulfill the vacancy which is created because of rising air parcel. Now, one thing that you have to understand is, let's suppose we talk about the summer season in the northern hemisphere. Now, when you have the summer season in the northern hemisphere, sun almost shines over the region of Tropic of Cancer, right? So in that situation, the absolute largest or the greatest amount of heating will not happen at equator. It will happen to the north of equator. For example, on 21st of June, that is when we have the summer solstice. Now, the position of the sun is over Tropic of Cancer. In terms of the region of India, it is above the region of central India. So central India will be much more hotter. Northern India will be much more hotter as compared to the region of equator. Now, what does that mean? That means it will be the region around somewhere in India. That is where you will have the absolute low pressure which is created, the thermal low pressure which is created. So these pressure belts, they are not fixed. These pressure zones, they are not fixed or fixated. In the sense, when you have summer in the northern hemisphere, this entire aspect or this entire fixture of equatorial low and the ITCZ, this ITCZ during the summer can move maybe somewhere here. It moves north. Now, if the ITCZ moves north, so think about it. The winds that will rise up from the ITCZ, the air that will rise up from the ITCZ will fall and eventually sink somewhere further away. And this entire pressure belts and the pressure zones, all of them will continue to shift. Again, in the months of winter, when it is summer in the southern hemisphere, position of the sun will be somewhere here in the southern hemisphere. So the ITCZ will be shifting south. Along with that, all the pressure belts, they shift to the south. So that is what is observed. And that is what leads to the generation of winds across the planet. On the surface, if you will observe, you have a wind movement happening from 30° to 0°, from 30° to 60°, and from 90° to 60°, you have a continuous wind movement happening on the surface. Right? So this model is able to explain ably well what are the various different types of wind patterns, etc., which are in existence overall. Okay, once again I will repeat it, so listen to this carefully once again. So here, what is this tricellular model of circulation about? So basically, this gives you an idea, or this gives us an idea about the air circulation which happens, and where around the region of equator there is substantial amount of heating. That substantial amount of heating, basically because of high solar insolation, you have the air which starts to rise up. Now when the air starts to rise up, it creates a kind of a low pressure on the ground. It is a thermal low pressure, and that is what is referred to as an equatorial low or an ITCZ. As the air rises up from the region of equator, basically upon hitting the region of tropopause, that is when it will diverge. One part will go into the southern hemisphere, other part will go into the northern hemisphere. Now let us consider only the portion of the northern hemisphere for easier understanding. So when we talk about the portion of northern hemisphere, or the upper air movement happening in the northern hemisphere, so if I were to use this image to indicate the upper air movement, think about it. Air would rise up around the region of equator, isn't it? They would rise up at the region of equator and basically would be bending to the right in the northern hemisphere. So overall, you will observe that around this area, somewhere around this area, there is an increased concentration of air and accumulation of air, which is happening in the region of upper troposphere. Right? The winds cannot move further north because of so much amount of bending. It cannot be possible that this air parcel moves to the region of the poles. It's simply because of the bending, it starts accumulating there itself. Now, then what happens? After that, when it accumulates significantly, that air starts to sink. And it sinks, it hits the ground at the region around 30° north. And that is when you experience a high pressure on the ground. But this high pressure which is exerted, which is experienced, that is a dynamic high pressure. That is not a thermal high pressure. But why dynamic? Because it is purely a high pressure by virtue of the sinking air. If it would have been controlled only by temperature, 30° north still experiences a higher temperature. So it is purely a dynamic pressure zone. Now, when the air hits the ground at around 30°, it diverges. One part goes towards the equator to fulfill the vacancy created by the rising air at equator. One part continues its journey towards the region of the poles. Now, meanwhile, in the region of the poles, you have such a high pressure and a very strong high pressure which is created because of very cold conditions at the region of the poles. It is also a thermal high pressure, which we refer to as the polar high. Now, that polar high means there is a sinking air, and that polar high also means that air will start moving from the poles towards the lower latitude. Now, this polar wind, it interacts, it basically converges with the wind coming from 30 degrees. And here at the region around 60°, that is where the convergence happens. And in this convergence, eventually the air from the tropics and the air from the poles, they converge and they rise up. When they rise up, then they will again hit the region of tropopause and again they will diverge. So that is how you attain the three cells. They are named as the Hadley cell, which is a thermal pressure created cell. They are referred to as the Ferrel cell, which is purely dynamically induced cell. And you have a polar cell, which is also partially controlled by the thermal factor, because if the polar regions, they have the high pressure, it is purely by virtue of very cold temperature conditions. So accordingly, you have the creation of these pressure zones or pressure areas. So you have Subtropical high pressure belt, subpolar low pressure belt, polar high, and equatorial low. These are your various different pressure zones which come into existence. So here you will observe thermal pressure zones. They are two. That is ITCZ and polar high. Then dynamic pressure zone. That is also two. That is subtropical high pressure high and subpolar low. Okay. Now, why is it that when we talk about these pressure zones, remember that they are not fixed in the same place. Always remember this. It is other than the polar high, all these pressure zones, they can change, they can shift. When it is summer in the northern hemisphere, the ITCZ in itself, because ITCZ represents an absolute low pressure, thermal low pressure. That is a low pressure created due to intense heating. So that is why when it is summer in the northern hemisphere, that equatorial low in itself shifts northwards. And as that shifts northwards, the subtropical high pressure belt will also shift northwards, the subpolar low pressure belt will also shift northwards. Subsequently, in the southern summer, that is when you have summer in the southern hemisphere, the ITCZ, or when the sun is basically shining directly over the southern hemisphere, the ITCZ also shifts slightly to the southern hemisphere, and all the related pressure belts also shift to the south. Why is it referred to as ITCZ? Because when we talk about the region of equatorial low, this is where you have winds coming from the tropics, that is the 30-degree from both the hemisphere, that is considered to be the tropical region. So from the tropics, the winds are converging around this low pressure. And that is why this low pressure is also referred to as the intertropical convergence zone, because tropics and winds from tropics from both the hemispheres are converging in this area. Is that understood? Or is there any doubt which prevails? Okay, good. So now here you have the image of these particular, the tricellular model of circulation. This is just to give you an idea about how this circulation is facilitated. So you have the Hadley, Ferrel, and the polar cells, which are significantly important in order to attain this circulation. But you have to understand that on the surface, what is the wind pattern? Right? On the surface here, when we talk about the surface winds, so you have wind moving from subtropical high pressure to the equatorial low, or ITCZ. That is, you have winds from 30 degrees to 0 degrees, right? Then you have winds from, again, subtropical high to subpolar low, that is 30 degrees to 60 degrees. And then you have wind pattern from 60 degree to, or basically 90 degree to 60 degree. These are the surface winds which are in existence. Okay. The three cells can be related with three layers like troposphere, stratosphere, and mesosphere. How? In what manner can you relate these three, Hadley, Ferrel, and polar cells, to the stratosphere and mesosphere? Please enlighten me. What is it that you are formulating in this? Is this portion clear? For others, is this portion clear? Akshay, why is it named as Ferrel cell? Based after the climatologist that we talked about. We talked about the climatologist William Ferrel, who basically discarded the unicellular model of circulation by Hadley and the arguments provided by Ferrel that we discussed. So that is why this Ferrel cell basically came into existence. The three cells can be related with three layers like troposphere, stratosphere, and mesosphere, the movement of wind or air. So, Akshay, you might have joined late, so that is why you missed that. The movement of wind. Parshuram, my dear friend, I'm unable to understand the question that you are asking. That this entire movement of air, right from the time of, right from the portion of unicellular model, if all the discussions that we are having only about troposphere. Where did stratosphere and mesosphere come into the picture? We have talked about the fact that air rises up. In majority of the cases, the air will be stuck only up till the tropopause. So how can we have the circulation in mesosphere and stratosphere? So kindly put your question properly so that I'm able to infer, at least so that I can help you get rid of that doubt. Utsav, why air has a tendency to fill the vacancy? Balance, always balance. So whenever you have a region of deficiency, something from a surplus area will always go there. Okay, try doing one thing. Try, if you have ever seen lot of those small thermocol or styrofoam balls that you have, which is used for packaging. Now you put that bag of thermocol balls, you tear that packet, right? You make a small incision. All those thermocol balls will start coming over, remove some portion. More will come over, remove some portion. As soon as they gain balance, again remove some portion. More will come. Why? In order to gain balance, in order to maintain that balance. I'm not able to understand why only three cells. Okay, okay, so that is your doubt. You wanted more cells of circulation, is it? Okay, now I understood your doubt. What is your doubt? Okay. So this is very simple, in fact. See, why will you have four cells or five cells? What can be the logic behind it? See, even these three cells, it is not as if three is very unique number. So let us have three cells. Understand the logic. Logic is very simple. Polar and Hadley cell, they are created due to the thermal pressure. That is equatorial low and polar high. Now you have the cells of circulation in the polar area, in the equatorial area. You have these cells of circulation which is happening simultaneously. Now, in between them, if you think about, I'm sure you would have basically seen the operation of a gear mechanism. If I can replicate that, obviously I won't be able to. If I have, let's suppose, if I have three of the wheels which are joined with each other, all of them are joined with each other. If I rotate this and if I rotate this, or in another direction, obviously, if I rotate this like this, the first wheel, if I rotate the second wheel, will this one also not automatically start rotating the middle one? It will start rotating by the by the movement which is induced in the first and the second wheel. The middle one will automatically come into rotation. So the Ferrel cell which is created, Ferrel cell is created purely because of the existence of these thermal pressure zones, thermal pressure cells in the form of Hadley and the Hadley and the polar cell. The Hadley and the polar cell, they are driven by the thermal pressures, and because of their generation, in between them, there is another pressure or another movement of air which is induced, because in the region around the subtropical high, you have the Hadley cell has got a sinking air. So here also the air accumulates and sinks along with it. Here also in the polar cell, you have the air basically rising along. Here also you will have that as the Ferrel cell. Now let us for a moment entertain your concept of having five cells. Why only five cells? Why not 10 cells? Why not 50 cells? But it is not the individual cells of human body that we are making. We are not designing it like this. This is something that we are trying to understand, that how the circulation takes place, how the air circulation takes place. How can you come across at a region of 5 cells? Let's entertain that thought for a brief moment. So here you have the air, but the air will sink where? In upper atmosphere. Where will the air sink? It will always sink around 30 degrees. Why only at 30 degrees? Is there something special around 30 degrees? Because of bending due to Coriolis force, that is where the air will start accumulating if it has risen around the region of equator. So the air will settle at around 30 degrees. This is your one cell complete. Then at the region of the poles, you have winds which are getting generated, right? Winds are getting generated. Now, either these two winds will meet here between the tropics and the poles. Where will they meet? Where is it? Ideally, that a wind generated from 30 degree and a wind generated from 90 degree, if both the winds are moving, where should they meet? Should it be the case that the wind generated from 90 degree will exist only till 80 degree north, and the wind generated from 30 degree will exist only till 40 degree north? Can that be the situation? No. Why? Why is it that the wind is converging at 60 degree and rising up? Because the winds from the polar areas, they are also traveling, because that is also a high pressure. The wind from 30 degrees, they are also traveling because that is also a high pressure, right? Now they will have to converge somewhere. Without convergence, why will they rise up? From 30 degrees to 90 degrees, across the planet Earth, from 30 degrees to 90 degrees, will you come across any situation where there will be a polar low pressure or a thermal low pressure which will get created? No. No, none of those regions get so heated up that a thermal low pressure can get created. So that means only a dynamic pressure can exist in between those areas. So dynamic pressure will get created. Why? Because of the convergence of the winds. Where will the convergence of wind happen? Take an average of 30 degree and 90 degree. It comes midway at around 60 degree. That is where the convergence is happening. Are you able to understand that? Or is it the case that I am not able to understand your question? It has got nothing, absolutely zilch, zero to do with the portion of stratosphere and mesosphere. If you are thinking that three cells, so stratosphere, mesosphere, what about thermosphere and exosphere? Why not another cell for ionosphere? It has got absolutely no relation with it. It is very similar, if I have to provide the analogy, that these three cells of circulation are there because, we were three brothers and we had a lot of brotherhood amongst us. So that is why three cells of circulation. So it is absolutely absurd, isn't it? So that is basically the cells of circulation that you observe. It is driven by the realities on the ground surface. It is not the case that few scientists sat on the table and they started drawing. Okay, Hadley, we will give one cell to you. One cell we have to allocate to Ferrell because that is the person who basically junked your theory. One cell will give to polar area. Why not we let us give one cell to Modi ji also, that we have Modi circulation also. That is not how it works. It is basically the thermal heating which is created. That thermal heating at ITCZ induces that circulation. The cooled conditions at the polar region, that induces a circulation. In between these two, there is another circulation, and that is the Ferrell cell circulation. Okay, I think that is all that I can basically do to assuage your query about this. Otherwise, beyond this, we can keep on competing each other about absurdity, that who can get more absurd. Does it mean in southern hemisphere conditions are different? Why? Why do you come to a conclusion that in southern hemisphere the conditions are different? Southern hemisphere, the conditions are absolutely the same. That is why it is a mirror reflection in the southern hemisphere which takes place. Why do you think that in southern hemisphere the conditions are different? Actually, what I'm trying to do is I'm trying to understand the genesis of question in your mind, that what might be the concept that you would have understood that you have this question, that okay, so in northern hemisphere he has shown us, in southern hemisphere he has gone silent, so maybe southern hemisphere something different is happening, something very fishy is happening. Benjita, easterlies explain Sir, explain easterlies. Benjita, we have not done westerlies, easterlies, trade winds. So, first of all, you explain what are westerlies and trade winds, doldrums, horse latitudes. I will then explain what is easterlies. Okay. So, here, basically, Priya, what I will do is, see, this is something which you should be able to deduce naturally. 0 degree, 30 degree north, 60 degree north, 90 degree north, 30 degree south, 60 degree south, 90 degree south. So here you have a circulation like this. Here you have a circulation like this. Is that now understood? Is it now clear? Ganesh will come to cloud formation later on. That cloud formation is always associated with a rising air column. And if I talk about cloud for a brief moment, I will have few questions all the way that please explain cloud formation again. So when we come to the clouds in the immediate next module, I'll talk about it. Means the pattern is different because more of the water body in the southern hemisphere. Okay. See, understand this. When we talk about the southern hemisphere, you have a kind of a uniformity in distribution of temperature, right? And it is the thermal driven pressures are present in the Hadley cell and the polar cell. So around the region of equator, in the southern hemisphere also there will be heating. Around the region of poles in Antarctica, there will be very cold condition. So polar cell will be in existence. Hadley cell will be in existence even in southern hemisphere. So in between them, you will have a Ferrel cell also coming into existence in the southern hemisphere. Okay. So that is something which is very similar in the southern hemisphere. We will come to it that what happens in reality actually. This is what happens on a bookish manner, which created that doubt in Parshuram's mind that why only we are going with 3, we should have at least 5. 5 is auspicious, so we should have at least 5. So that is not the case. This is actually something that we see, that is the theoretical aspect of it. Once you observe this on the ground surface, we will talk about it. Now, we have seen that on the surface, you have winds moving from 30 degree to 0 degree, from 30 degree to 60 degree, and from 90 degree to 60 degree as well. So here, if you analyze this, basically, on the planet, on the larger scale, let us represent this as the ITCZ, this as the region of 30 degrees, this as the region of 60 degrees, and this will be your 90 degrees. Okay. Now we have seen that on the surface, the movement of wind happens from 30 degree to 0 degree. 30 degree to 0 degree. So ideally the wind movement should happen like this. But it will be impacted by the Coriolis force. So it will bend to the right. It will bend to the right. Here. Okay. Now, in the southern hemisphere also very similar, that the winds are coming from 30 degree to 0 degree. So here also it will bend to the left because we are in southern hemisphere. So this one will bend to the left. Now these winds, they are known as the trade winds, okay, or simply trades. Why? Because historically, these winds have been used by many sailors, merchants, mariners, etc., in order to facilitate the movement of the ships. So that is why this is a name which has been associated with this for a very long period of time. That is why the trade winds. Generally, when we name the winds, the naming of the winds is always done either on the point of their origin, the direction of their origin, or the region from where they are originating. If a wind is originating from the mountain, we call it a mountain breeze. If a wind is originating from a land, we call it land breeze. So similarly, the direction from which the wind is originating, that is used as the methodology to name the wind. So here you will find that the wind in the northern hemisphere is originating from which direction? Northeast direction. Northeast to southwest is the movement of the wind in general, isn't it? Northeast to southwest. So that is why in the northern hemisphere, these are also referred to as northeastern trades. Okay. In the southern hemisphere, you will observe that the wind is from southeast to northwest. So these are also what are referred to as southern trades or southeastern trades. Then we have a wind motion from 30 degree to 60 degree. From the subtropical high to subpolar low, you also have a wind motion. So here, in this wind motion, what do you observe? Here it will get bent, obviously in the rightward direction. So this wind motion will be like this. Okay. In the southern hemisphere also, from 30 degree to 60 degree, but it will be bending to the left. This will be bending to the left. So what do you have? These winds appear to move from west to east. That is why they are known as westerlies. These appear to be moving from west to east, and hence they are named as westerlies. Now you have a wind motion from 90 degree to 60 degree also in both the hemispheres. So how will that happen? Again, rightward bending in the northern hemisphere. Now these winds appear to be coming from east to west, and hence the name easterlies, because that is where they are originating, in the eastern direction. They are basically referred to as the easterlies. Okay, or also referred to as the polar easterlies. Now these wind systems across the planet that you see, they are in persistence, they are in existence throughout the year and across the planet. And hence these wind systems, they are also what are referred to as the permanent wind systems. Okay, these are what are also known as the permanent wind systems. Here, if you take a look at it, this is basically the overall encapsulation of these permanent winds. You have the trade winds between the subtropical high and the ITCZ. You have the westerlies between the high pressure and the low pressure, and you have the polar easterlies furthermore. So like that, you have the trade winds here also, westerlies, and the polar high also. Now, the pressure zones, the pressure belts that you see, that is the subtropical high, the ITCZ, when we talk about the subpolar low, when we talk about the polar high, other than the polar high, all the other pressure belts, they can move, they can shift. When the sun is, let's suppose, here in the northern hemisphere, then the ITCZ will also shift north. As the ITCZ shifts north, all the Hadley cell will shift north. So the subtropical high pressure belt will shift north. The subpolar low pressure belt will shift north. As the ITCZ shifts north, from here also in the southern hemisphere, it will shift north. Here also it will shift north. And then when the sun shines in the southern hemisphere, all of them will have their shift to the south. So that is how these pressure belts, they can undergo a shift in the various different seasons. So pressure belts, pressure belts shift to the north during northern summers, right? Why? Because of shifting of ITCZ. Shifting of ITCZ. And they shift to the south in the southern summers. South in southern summers. Okay. Now these pressure belts, they are also known by certain alternative names as well. Many of the times the candidates are much more interested in knowing those names. Okay, but overall you should pay attention into understanding the phenomena behind it, the principle behind it. So if we talk about the alternate names of it, we start first of all with the subtropical high pressure belt. The subtropical high pressure belt, that is subtropical high pressure belt. Now, this is also what is referred to as the horse latitude. Right? Why? Because if you talk about the region around 60 degree, or rather 30 degree is where the subtropical high pressure belt is, here you have a sinking air. In that very wide area, it is not as if that sinking air will happen at this point. So if I will stand here, my one leg will be on the other side, one leg will be on the other side. No, it is in that entire zone where you experience that sinking. That zone can have a width of 50, 100 kilometers or even more. So in that area you have the sinking air, and that sinking air eventually diverges. But let's suppose you are an individual captain of a ship, right? The ship which is going to move only with the help of the sails. That's it. You don't have any engine associated. So, in that case, you don't have any wind movement. Will you experience any wind movement at all? Absolutely not. You will be standing where you are, right? Or the ship will not be moving. So, what used to happen in the early days when the captains of these ships would come across these areas, they would basically encounter this absolutely calm condition. No rainfall, absolutely no rainfall, no wind movement. So, their ships would lie stable and stagnant in the same region for a long time. Now, in those days, the ships would also, and the traders would carry a lot of horses in their journey, because eventually when they would reach the ground, they would have to use those horses in order to travel, and also basically for trading purposes also. So eventually what they would do, that when the ships would be calm for the same in the same area for a very long time, they would need to conserve the resources, more importantly water. So what they would do is they would simply throw the horses overboard. They would basically kill them, throw them in water. Now, the other aspect of it was also the case that if you would throw multiple horses at the same time, you would come across a situation where some splash could be created in the water so that the ship gets some movement. And then after that, maybe the wind picks up and maybe further the ship can move. That is why these latitudes around the subtropical high of calm conditions, they have been named as horse latitudes. Okay, that is the reason why they are named as horse latitudes. Then the ITCZ, that is also referred to as the doldrums. This region, the equatorial low, this is also what is referred to as doldrums. And why is that the case? That is because in this area, you will observe that there is, let's suppose like this, in this area, you have wind which is coming from both the tropics, the wind is then converging and rising up. Okay. Now, if you are an individual standing at the point A, let's suppose this place A, you will experience a very strong wind movement coming across your face. If you are an individual standing here at the place B, again, you will experience very strong wind movement, right? Happening around you. But what if you are an individual standing here at the region C or region Z? Here, will you experience any horizontal wind movement at all? Absolutely no. So at this region, exactly at the region of this doldrum, you won't find, or this region of this low pressure, you won't find any horizontal wind movement. And that is why this is referred to as a kind of a doldrum, a still condition, so to say. So, lack of horizontal wind movement. That is why doldrum is also used nowadays for a long period of time now. Doldrum is also a terminology which is used for in English language as well, right? That the preparation is stuck in doldrums, right? The governance is stuck in doldrums, so means not going anywhere. So that is where this is named as the doldrums. Okay, now so this is basically the concept about the pressure belts and the permanent winds. But as I told you, in real world, actually, it is not something which is replicated out there in the real world scenario. Out there, it is something which happens in broken frame. You cannot have the situation where, like a belt that you wear, the similar belt you have all across the planet. That is not how it works. So let us take a look at what actually this high pressure and low pressure, what does it look like in real world, in actuality. So here we have the isobaric representation across the globe in various seasons. So this is the month of January. Here, this is your January, and this is your month of July. First of all, I would want you to observe the equatorial low or the ITCZ. Look at the low pressure. So the ITCZ is not at all straight. If I were to draw it by an imaginary line, the ITCZ bends here. Why? It is the month of January. It is the summer in the southern hemisphere. So rather than here at equator, Australian desert will be much warmer. So that is where the thermal low pressure will exist. So that is where the ITCZ bends over. Okay. Then look at the subtropical high. In southern hemisphere, observe. Now, Priya, this is what your question was. In southern hemisphere, you will observe that there is a uniformity of distribution of water. So all the pressure belts are almost uniform. So here you have the subtropical high. This is also the South Pacific subtropical high, the South Atlantic subtropical high. So rather than these large belts, you have the pressure zones which are in existence. You have zones of high pressure and zones of low pressure. Winds will move from a high to a low always. Okay. Now this southern Indian Ocean high, later in the month of June, July, August, this becomes a driver for the Indian monsoon. We'll come to Indian monsoon later. Look at it in the northern hemisphere. The high pressure here, high pressure is here, high pressure is here. Okay. Then you have Siberian high here. This is, by the way, winter in the northern hemisphere. Okay. Now take a look. So it is from here, these high pressure regions, that the winds will originate, move towards 60-degree westerlies also. So westerlies will move up till where? Up till the subpolar low. So here you have Aleutian low, that is around the Aleutian Islands in this region, which is also, by the way, a region of very active volcanicity. So Aleutian low, Icelandic low. Here you have a substantial low pressure. Why? Not because of heating, because the polar winds are converging with the westerlies in this area, right? Here, that is the extension of the Aleutian low. In the southern hemisphere, you have again the circumpolar trough. Why? Because circumpolar means all around the poles in a circular manner. So this is quite uniform because surrounded by water bodies from all sides, then Antarctica being a continuous and a uniform landmass. So that is why the winds will be converging almost equitably all around the poles. That is, the polar winds and the westerlies will be converging almost equitably. So that is where you will have these low pressure. Okay. Observe the month of July. In the month of July, observe first of all the ITCZ. Here you have the low pressure. Here there is low pressure. But now we are in summer season in the northern hemisphere. Obviously, the region of Sahara, the Arabian desert, will get much more heated up. This is where the low pressure lies. In over India, the ITCZ during the summer months that passes through the northern portion of India. So this is your low pressure. Then you have the high pressure here, the subtropical high pressure. Observe, as compared to the previous one, all of these have slightly moved northwards. All of these have slightly moved ever so northwards. Okay. Observe this. This is the Hawaiian high, the tropical high pressure, the subtropical high pressure in the northern hemisphere, Hawaiian high, then Azores high or Bermuda high, named after the group of islands in this region, right? So this is your subtropical high pressure. Then you have the low pressure. Icelandic low pressure gets deviated ever so slightly. So, like that, you have the presence of these pressure zones. So, you have, by the way, when it is winter in southern hemisphere, in the month of July, obviously the region of Antarctica will get very cold. So, the polar high pressure in southern hemisphere will get very strongly. Okay. So, that is basically the pressure zones which get created and the movement of winds which are induced. It means in this time, sailing a ship is little difficult due to high pressure in. It means in this time, sailing a ship is little difficult due to high pressure in southern hemisphere. The question that you guys are asking, you're framing it in such a way. Please, could you simplify this? That sailing a ship is difficult due to high pressure in southern hemisphere. What is the meaning of this? Please simplify this. So, Benjita, now do you understand the portion of westerlies? Akshay, are all these air circulation concept and pressure wind forces connected to satellite launching or other spatial activities in India as Sriharikota comes in alignment of equator? The reason why we launch the satellite, always the satellite is launched in a direction from west to east, always. And why is that? That is something that we covered in the first module and the first class itself. And always the satellite launches are done as close to the equator as it can be. Why? Because the rotational velocity of the Earth is maximum around the region of equator. So as the rotational velocity is maximum, if the Earth is rotating, if you manage to launch a satellite in the same time, the rocket will gain the additional velocity of Earth's rotation. It will be an added relative velocity. So the rocket will be able to move much faster. That is why always it is launched as close to the equator as you can. And always it is launched in the west to east direction, again, in order to add on or capitalize upon from the rotation of planet Earth. That is what is used for the launch. Westerlies, etc., they never come into play when you talk about the satellite launches, because within a few seconds or within, let's say, 30 seconds, the satellite very truly and significantly crosses the region of troposphere. Okay. So it means in this time, sailing a ship is little difficult due to high pressure in the high pressure zone in southern hemisphere. So now you don't have the sail ships anymore, do you? Now you have the diesel powered or the nuclear powered ships which are there. Now you are no longer dependent on the sailboats, that if there is some amount of wind, then we will have that sail. Okay, I hope you understand. Okay, any other doubts that you have? No? Okay. So now we move forward. Now we talk about the local winds. So when we talk about local winds here, so we have seen earlier the case of the permanent wind system. Permanent wind system is basically when you have winds which are blowing all throughout the planet throughout the year. They are referred to as the permanent winds or the planetary winds. They are moving all across the planet and they are moving consistently throughout the year. But you have certain winds which are moving only over a certain area of the planet, small area of the planet, and they are in existence only for some portion of the year, only for a small duration during the year. So those particular winds which are in existence only in some portions, and that too for some restricted part of the year, these are your local winds. So when we talk about local winds, they get into existence, are in existence only in some areas, are in existence only over certain areas and for a short time duration. Okay, these are your local winds. For example, Lu, what you observe blowing over the Indian subcontinent during the summer months, the northern portion of Indian subcontinent in the summer months, that is Lu, right? So, for example, when we talk about the various different winds such as land breeze, sea breeze, etc., that is not something which is in existence over the entirety of the planet Earth. That is in existence only over some portions, right, across the coastal areas. So that is what we know as the local winds. Now, in your examination, from your examination perspective, these local winds, the idea of it about land breeze, sea breeze, you can get mains type of question as well. But generally, in these local winds, you get a question about the region where they are moving, whether we know of them as the warm wind or a cold local wind. Okay, now I have provided to you a list of all those winds as well, which and the continent wise list of all the winds, so that you can at least go through or have a perusal of it only for your prelims perspective. That list would be sufficient, that I have provided in the PPT itself. But when we talk about local winds, the broader classification can be done into daily winds, for example, land and sea breeze, and also mountain and valley breeze. And when we talk about the regional local winds, they move over a particular area. For example, Lu blows only over India. Lu is not something which is the phenomena world over. Then Chinook blows only over the north portion of northwestern part of North America, not anywhere else. Phone in the region of Swiss Alps, that is the Alpine region in Switzerland. Then Mistral over the region of Mediterranean, originates from northern Africa, moves across basically, or rather in the case of Mistral, it moves over the region of France and Spain. Then you have Sirocco, which moves over the region of Mediterranean. You have many of them. You have, for example, Blizzard, you have Black Roller, you have the Harmattan, you have Veld, you have many different types of local winds. Okay. Now here, when we talk about these local winds, we'll take a look at each one of them, majority of them, not all of them. Now let us understand the basic principle involved. So for example, when we talk about the land and the sea breeze, now here, this occurs on a very local scale, on a very small scale. That is, as you can see here from the image itself, the entire extent of this wind movement or the breeze movement is happening only across the width of 50 kilometers, not more than that. Okay. Now, here, another thing that I want you to concentrate upon, I want you to understand is the fact that when we talk about breeze, for example, what is breeze and how is it different from wind? So, wind which moves, the air which moves, it moves with different velocities. When it moves very slowly, that is when we refer to as breeze. Okay, when its speed is very, very slow, that is what we refer to as breeze. When it moves comparatively, significantly very fast, that is when you encounter it as gales, right? So you have various different types of parameters of the naming based upon the speed of it. So breeze refers to very light movement, very slow movement of the air, okay, with very little speed. So that is your, when we talk about land and sea breeze. So why do they occur? They occur on a daily basis. If ever and whenever you have visited the coastal area, if you recall your time when you were standing at the coastline, you would have observed that the basic wind would either hit your face or would come from behind and move towards the sea. Right? It creates a very pleasant scenario at the coastline. So why does that happen? So let us understand what actually pans out during the afternoon, during the daytime. Basically, we have seen when we were talking about the presence of or the heating of land and water taking place at a different rate. During the daytime, we do know that the land area will get much hotter. Why? Because the land gains heat at a much quicker pace as compared to the water body. So the land gets hotter much quickly. So when the land becomes very hot, that is where you have a low pressure which gets created. Meanwhile, the water is comparatively cooler. It is not cold, comparatively cooler. So the water, you will experience the presence of high pressure. Okay, so you have a low pressure over land, a comparative high pressure over the water body. Winds always blow from a high to a low. So the winds will be blowing from that high pressure to that low pressure. And that is where you will observe the wind moving from the sea towards the land. And because it is originating from the sea and then moving over to the land, that is why this is also referred to as sea breeze. Because remember, we talked about the fact that the winds are named depending upon the direction and the position that they originate. So this is what we refer to as the sea breeze. Okay? It is originating over the sea during the day. Why? Because sea is comparatively cooler. So a comparative high pressure would develop. Now, what happens during the night? So during the night, you would observe that the land becomes much colder during the night. Water is comparatively warmer. We had talked about it yesterday itself. So when the land becomes colder, right? So here you will have the high pressure. Water, when it becomes warm, it is comparatively warmer. So this is where it is low pressure. So here again, you will have a circulation of wind moving from land to sea because it is originating over the land area, hence the name land breeze. Is this understood? In southern hemisphere summer, why the pressure belts have more distance from equator? Sridevi, in some southern hemisphere in summer. Okay, are you talking about the month of January or are you talking about the month of July? Which summer are you talking about? Are you talking about the month of January? Please specify the questions, please specify. Please understand that it might be possible. I know it is very difficult to think about it, but it might be possible that all of us, we are not thinking at the same level. So it will take some time for me to reach your level of thinking ability. So please help me out, feed me out those particular basic crumbs so that I can come to that level. Yes, in the month of January. Okay, so you're talking about the fact that in southern hemisphere in summer, the pressure belts have more distance from equator. Here, see, here the pressure belts are much closer. Here the pressure belts, they are much closer to the equator. Why? In the month of July. Here it is comparatively far away. Why? Because in these months, in the month of July, it is summer in the northern hemisphere. Summer in northern hemisphere. Because it is summer in northern hemisphere, what do we have? Pressure belts, they shift to the north in the summers due to shifting of ITCZ. So here observe where the ITCZ is. The ITCZ, if I have to draw a kind of a rough line, ITCZ passes through here. So this is where the Hadley cell will be in existence. So obviously it will be much closer to the region of equator. In this case, we are talking about the summer in southern hemisphere. So in that case, all the pressure belts will shift to the south. That is why this high pressure will also shift slightly to the south. This will also shift slightly to the south because it is summer in the southern hemisphere. Shifting of pressure belt. Is that understood, Sridevi? This happens only within 50 kilometers sea and land breeze, or is it some assumption? Basically, it happens, the sea and land and sea breeze that occurs in that range itself, around 50 or sometimes even less than that for that matter, 45, 40 kilometers. That is the entire extent of it. This is not like your planetary wind system. This is something which is experienced over a very small area. Okay, I hope that is understood. Now we come to another wind. So land and sea breezes, they happen on a daily basis. Happen on a daily basis. Yeah, I understand some humming sound is coming. Basically, it is some construction is going on in the region of the office. So that is why you have that humming sound, or it is a drilling sound. We are trying our level best to keep it at cap. But when it becomes intolerable, please let me know. Okay, and offshore and onshore wind and land and sea breezes are the same. See, land and sea breeze, they are a kind of onshore and offshore wind kind pattern. But when we talk about onshore and offshore wind, Parshuram, we are basically referring to the westerlies, trade winds, etc. Now, when they are moving continuously over a region, they can have onshore impact also, they can have offshore impact also. Akshay, are you in Delhi Byju's office? No, my dear friend, I'm in Bangalore office of Byju's. Yeah. So now we come to the portion of mountain and valley breeze. So this also occurs on a daily basis. Occurs on a daily basis. So just like the case of land and sea breeze, between day and night, you have different temperature conditions in water and over land area. Here also, in the case of a mountain and a valley, you have different temperature conditions leading to different pressure conditions in the region of the mountain and in the region of the valley. So that also creates its own individual wind movement in a small area between the mountain and the valley. So here, during the day, what is experienced is generally by this mountain, we are not referring to Mount Everest. So don't think about this mountain as the Himalayan peaks which are there, but generally the normal heighted mountains which are there, a couple of thousand feet from the sea level, those kind of mountains, or 2,000, 3,000 feet, those kind of mountains. Now, during the daytime, the amount of solar insolation is very, very high on the mountain tops. We know that with altitude, the amount of insolation increases. So when the insolation is very high on the mountain tops, that creates a kind of a substantial low pressure due to heating, isn't it? That creates a substantial amount of low pressure. Now, this low pressure, comparatively, the valley bottoms will be slightly cooler during the day as compared to the mountain top, because the amount of insolation received will be slightly less. So that is what will put into motion a movement of the wind from the valley to the mountain top, right? From the valley to the mountain top. Now, these winds, because they are originating from the valleys, that is why they are referred to as valley breeze. Because they are originating from the valley, hence they are referred to as valley breeze. Now, during the night time, what happens when we talk about it during the night? So during the night, basically, the mountain top will cool down quite substantially, very fast. It will be very cold on top of the mountain. So that creates cold conditions or high pressure. Comparatively, valley bottom will be warmer. This creates a kind of a high pressure. Now, what it will induce is the origin or the movement of wind from here, from high pressure to the region of the low pressure. Okay, that will induce a movement from high pressure to low pressure, and this is basically originating from the top of the mountain. Hence, it is referred to as mountain breeze. Gaurav, sir, is breeze is the reason behind cloud formation? I understand the kind of impatience that you have to understand the cloud formation. All I ask out of you is give me around 45 minutes. I will talk about cloud formation. I will tell you why cloud formation takes place. I will, in fact, do you one better. I will tell you why cloudburst also happens. I will tell you how is it that in certain areas the clouds can create ice formations and ice will start falling. But just have some patience, my dear friend. Okay, I understand that cloud formation is one of those areas where a couple of you at least have been asking, will this lead to cloud formation? How is it that the cloud formation happens? Will that lead to cloud formation as well? Will cloud formation happen because of this wind or not? I understand the level of curiosity. I really appreciate it. But it will be absolutely grave injustice towards you if I make a conclusion right now that this is what leads to cloud formation. Some patience is all I ask. Okay, please, if that is not much of a hard work from your side. The water falls during the night time, falls more water. Again, the water falls during night time, falls more water compared to the daytime from this concept. The what? Okay, I can keep reading it again and again, but the meaning is not clear, my dear friend. The water falls during night time, falls more water compared to the daytime. It feels like a tongue twister. The water falls during nighttime, falls more water compared to the daytime. What is the meaning of this question? Then I will be able to answer your question. I can write it down in front of the entire class also, and I will throw it an open challenge. Whosoever understands the meaning of these questions, I'll do one thing. I spent so much time trying to understand the questions. I know I'll have to improve my English over a period of time, but then this is something which is beyond my reckoning as well. So the water falls during nighttime, falls more water compared to the daytime. Parshuram, my dear friend, please be kind enough. Okay, waterfall. Okay, so see, a couple of you were smart enough to think about it. Hmm. He's asking for waterfalls in the mountain valleys. I think I'll need a special session from you guys in order to understand the lingo. So I will have to arrange an extra class for that. So, so you are asking about the fact that the waterfall that you have in the mountainous areas, they will have more water during the night time as compared to the day. That is not the case. Okay, if that is your query, if I am able to understand that query perfectly, so yes, so that is the query. Thankfully, with all of your help, it is a combined effort. So I won't take the credit for this. So no, that is not the case, because the waterfall is happening in the valleys of the mountains. The waterfall happens why? Because you have a stream, a small river, etc., which drains through that area. Now there, the movement of the wind will never end up increasing the level of water or the amount of water which is flowing through. So that is something which is not going to happen. Okay, right? I hope that is understood. But I request all of you, please understand that my level of proficiency in English, um, even though for a long period of time I thought that the English proficiency level is good enough, but it is not at the level of proficiency which is required to get into the understanding of what you are asking. So please treat me with a kind of a kid gloves. Please think about myself as you have a younger sibling or a younger candidate in your family who are unable to understand or fathom what you are trying to ask. Put it in simple terms, broken terms. I will be able to comprehend it. Okay. So I hope that is taken care of. Before I arrange an extra class, especially with you guys, to understand the lingo and to get that lingo ingrained into my mind, it will take some time. So please have some amount of mercy and some grace. So now, after this, we come to the regional and the seasonal winds which are in existence across the planet. In this case, we basically are referring to those winds which are not in existence across the planet, which are actually in existence, which come into existence only in some small area, and that too for a limited time period. So these are your, again, in the category of local winds only, but they are restricted only to some small portion. So let us take a look at each one of them. Let us try to understand their individual properties as well. So when we talk about it, so the local winds and the regional winds in our country, we experience the wrath of it. That is Lu. Now, Lu blows during the afternoons. That is around from 2 p.m. to around 4 p.m., right? In the afternoon, in the scorching heat of the summer, you have these warm winds which are blowing over the northern plains. They don't move over the southern part of India or the peninsular part of India. No, the peninsular part of India is bereft of it. It basically does not experience that. It has only experienced in the northern plain region. And it moves in a direction of west to east. That loop you won't experience in the region of any other part of the continent, any other continent. This is basically a very India specific, or rather, the Indian subcontinent specific movement of wind. It is very dry, right? Absolutely lacking moisture. It becomes much more drier as it crosses the Thar desert of Rajasthan. And then it encounters or moves over the region of the Indian subcontinent. It keeps on getting drier and hotter along the way. So that is the property, or that is the phenomena of Lu. So it is an example of warm advection. Okay. Now, why does this Lu basically, or in fact, before that, many of you living in that part of the country, or living in the or having born and brought up in those areas to the north of Tropic of Cancer, you would have had your own personal experience where you are not allowed to go out in those times, or when you were basically children. At that point of time, your elders won't allow you to go out at that point of time, from 2 p.m. to 4 p.m., or basically from 1 p.m. onwards till late in the evening. Why? Because that wind is so warm, so very dry, it can immediately not only raise the temperature of the surrounding, it can instigate or lead to the occurrence of heat strokes as well in the process. Right? People fall ill. Many of them, if they don't basically realize that they have been suffering because of this, many of them sadly tend to lose their lives as well due to that prolonged heat stroke. So that is your Lu. So Lu is hot and dry wind, which blows very strongly over the northern plains of India and Pakistan in the month of May and June. So that is when it is in existence. That is when it is in the strongest part. The direction of motion is from west to east, and they are usually experienced in the afternoons. The temperature varies between 45 to a whopping 50 degrees Celsius. So you can imagine how high the temperature is. Now, even though here, basically, you have to understand that this is not something that UPSC will ever ask you in the GS portion. That why is it that Lu blows from only from west to east, or what is the genesis of this wind? But then, as we have been doing all along, we are more interested in you knowing the reason of it. If you know the reason why that Lu is in existence, you will never forget that Lu as well. So basically, I will very briefly summarize this idea in front of you, that why that Lu is in existence, why is it in motion around the region of both India, Pakistan as well. So basically, the genesis or the origin of this is from the region of Balochistan, the Sindh and the Balochistan area, right? Bordering Iran, that is in the portion of western Pakistan. That is where the genesis happens because of a localized high pressure. Okay, the subtropical high pressure that is still in existence. Now, why does it blow over India? So basically, during the day, that is during the summer months, the region gets heated up every day, day after day. It gets heated up. So it gains very high temperature. So if you talk about the Indian subcontinent, basically, let's suppose if we talk about the region of the Indian subcontinent here, the entirety of the subcontinental region. So here you have the genesis of some kind of a high pressure. Okay. Now, throughout the day, you have heating which is received, which is experienced over the Indian subcontinent. And due to that heating in this entire area, especially during the summer, due to that heating in this entire area, you have the creation of low pressure. Substantial amount of low pressure is created. Okay. Now, this low pressure which gets created is why? Because since the sun rises up early in the morning, it beats down upon the land. So by the time that you have a clock striking 1 p.m. or 2 p.m., by that point of time, it becomes very, very hot. It becomes an active and an acute low pressure. And when that active and acute low pressure is developed, then what happens? From here, the winds will move from high to a low. They will move, they will cross over the Thar desert of Rajasthan. And when they cross over the Thar desert of Rajasthan, at that point of time, these winds further warm up. They further heat up, they become much more dry as well. And then they move over to the entirety of the region. That is why the direction is encountered as west to east. And that is why the time period of it is generally in the afternoon after the prolonged heating has been received during the day. Okay. Now, that is the case of occurrence of loo in the afternoons of summer. I hope that is understood. Okay. So loos are not found in southern India? No. In southern India, you won't find the existence or the persistence of loo, only in the northern India to the north of Tropic of Cancer. I understand the Tropic of Cancer is absolutely incorrect as per my diagram. Okay. So that is where you will find the presence of loo. Is that the same case in North Karnataka? No. North Karnataka basically experiences smaller local winds or the regional winds which are moving in that area due to heating. And in general, in North Karnataka, you would observe that after some amount of heating, it can bring rains also, right? But the problem there is that the moisture supply source, that is the Arabian Sea or Bay of Bengal, the northern portion or the northern central portion of Karnataka is cut off from that moisture source by the Western Ghats. That is why that much rain is not received. But you have some small winds which are in existence. Okay. Loo generally is in motion from west to east over the northern plains of India. It is not in the southern part. Does UPSC ask about regional winds also? Yes. UPSC will like to ask. UPSC loves to ask these kinds of questions where whenever UPSC gets an idea, okay, this is an area which we have not asked questions from for some time and students might be ignoring it. It is a golden duck chase for that. Now then we come across Chinook. Now Chinook is a local wind which is in existence only in the region of North America, and that to the northwestern part of North America. So if I were to basically think about it, here, this is the region of the Rocky Mountains. Okay. Now here you have a local wind which blows like this across the mountain slope. This is what is your Chinook. Now Chinook alters the temperature and the climatic condition in the region. Okay, how? Let us understand that. So whenever you have any mountainous area, and the mountainous area will have the two sides, right? So here, basically, you have the windward side, which is facing the wind, and you also have the leeward side. Okay, in the case of the windward side, that is the one which is facing the wind. So here, the air or the winds are rising up. They are forced to rise up. When they are forced to rise up, they cool down. Okay, in the process, they cool down. And as they cool down, basically, why do they cool down? Because the air expands. The air is allowed to expand, so it will cool down. And water vapor also cools down, condenses into liquid water droplets, and Gaurav, can lead to cloud formation also. But I will come to cloud formation separately later on. So here it rises up. It basically then eventually, by the time that it comes here, the air would have become completely dry, because this is the portion where all the cloud formation and all the rainfall would have occurred. Now, by the time that the wind comes here, as it is moving down the mountain slope, here it is moving from a region of low air density, that is the top of the mountain, to a region of high air density, that is the bottom of the mountain. That is the movement from the top of the mountain to the bottom of the mountain. And in that movement, it undergoes what is adiabatic compression. So this is wind warms up, or rather air warms up due to adiabatic compression. Okay. And due to that adiabatic compression, as the air warms up, then it hits the slopes, right? Or the lower portion of the slopes. This warm wind has got enough temperature to start melting the ice and the snow at the leeward side of the Rocky Mountains, right? And hence, these winds are also what are referred to as snow eaters. Okay, so Chinook is basically warm and dry winds blowing on the eastern slope of the Rocky Mountains. Okay, so again, understand what happens. You have the Rocky Mountains in this orientation. This is the alignment of the Rocky Mountains. So it will have a west side, it will have an eastern side. So if I take a look at the cross sectional view of it, the winds as they will approach the windward side is the side of the mountain where the winds approach. So as the winds rise up, they will cool down due to the process of adiabatic expansion. It will cool down, but then again, as the winds come here, now here you might have a query that why will the winds come down the mountain slope? Why can't we have the condition that the winds from here itself, they take a lift off, they should fly into outer space, they should have their own jolly good time? But that is not how the winds operate. Because of the force of gravitation, the winds are basically going to hug the ground surface. They are going to stick to the ground surface. So here the winds come down. As the winds come down the mountain slope, basically they are going to a region where there is significantly greater amount of air density, so they have to compress themselves. So this undergoes adiabatic heating, and that raises the temperature. So this becomes warm and dry, and this is enough to melt the snow on the leeward side of the Rocky Mountains. And that is what it is referred to as Chinook and is referred to as snow eaters. Okay. So that means the phenomena of previous year question paper doesn't work. It does work, my dear friend. Analyzing previous year questions will help you. Understanding the areas where, and also see, analyzing the previous year questions also help you understand the language that UPSC plays with. That is very important to understand. You might read a particular chapter 500 times, but then the UPSC has got a certain knack of playing with the words here and there, misplacing one word with another and doing the same with the other. So then you, once you get hold of that, that is why you come across candidates. Once they crack the code of it, once they understand the pattern of it, you will find that the candidates on a serial basis, they will score, okay, in the first attempt I got 120 in prelims, in the second attempt I got 125, in the third attempt the performance was very poor, I got 115. Like that, they will consistently be clearing the prelims examination because they are able to crack that code. So that is why previous year question is always advisable. Gaurav, why there is adiabatic heating? Adiabatic heating is caused because as the air comes down, as the air sinks down into the region of higher air density, the air has to compress itself. I hope we are aware. Okay, I took a shortcut because I thought that we were clear with this. So let's suppose when we talk about this particular area, air density is very low in this area, right? So the air will have an expanded volume. But here the air density is very, very high. So the air to come to this region will have to compress itself. And that compression will lead to heating. Windward side of Rocky will get monsoon effect, will get rainfall. Monsoon is different. Monsoon is what is referred to as a seasonal reversal of wind. The windward side of the Rockies will receive rainfall, will not receive monsoon. Okay, right? Is that understood? We have Arabian Sea as well in Western. Doesn't it affect Loo formation at such enormous levels? No, it does not, because in Arabian Sea at that point of time is busy dealing with cyclonic formations at that point of time in the month of late May. And also The high pressure that I told you in the region of Sistan Balochistan area, there some portion of that wind from Arabian Sea goes there. It causes some precipitation in that area, very little amount of precipitation, but whatever moisture is brought over, that moisture is lost by the time these winds cross over to the region of Thar desert and so on. That is why the wind becomes so very dry. Okay, then we come across what is referred to as phone. Now phone is a local wind that you find in presence in the region of Europe. Okay, it has got a very similar property, the same principle involved as is the case of Chinook. The only difference is, rather than the Rockies, here you have the Alps, and than the west and the east slope, here you have the north and the south slope, because the alignment of Alps is basically like this. Okay, so that is why here again, when we talk about this phone, so warm and dry wind like Chinook is called phone along the northern slopes of the Alps mountain. So let's suppose these are your Alps. Then basically on the windward side, if this is your southern slope, this is your southern slope, this is your northern slope, windward side, you will experience rainfall or snowfall in this case. And then here, the air will get warmed up and this will start melting the snow, creating warmer conditions. Please understand that when we talk about this region of Europe, it is very, very cold, right? We are talking about the region of Swiss Alps. So in this area, when you have these warm winds, it is not as warm as you have the Loo of 45, 50 degrees Celsius. Here in Europe, warm is, even if it is 10, 15, 18 degrees Celsius, it is considered to be very warm. And people, they bask in that glory of these warm winds, that okay, the conditions have become very, very pleasant. But the principle involved is very similar to that of Chinook itself. So these are more common during the months of spring and autumn in Switzerland. The weather becomes quite pleasant in the valleys due to the melting of the snow. Why? Because this will bring about heating, melting of snow. Melting of snow. Okay, that adiabatic compression and heating will happen. So therefore, the valleys of Switzerland are also called climatic oases in terms of providing relief from everything which is frozen around them. Now, when things melt, when the region melts, when you have the snow melt, then automatically in this area, it becomes much more favorable for various crops, etc. So early sowing of wheat can be achieved, ripening of grapes, and even the frost which develops generally during autumn on the ground surface, that is not experienced. So it has got a pleasant warming experience, that is phone. So Lu, phone, Chinook, three local winds we have seen till now. All of them are warm. All of them are dry. Okay? It is these properties that you have to keep storing in your memory. Okay? And you have to understand the region where they are moving. Okay? Chinook can cause rain in westward side of Rocky Mountains. Yes. Not only can, it will cause. But that is not Chinook. Chinook is the part of that wind when it moves to the this portion of that wind, this portion of the wind, that is your Chinook. On the leeward side, on the eastern side, that is Chinook. This portion, this is not referred to as Chinook. It is only when the winds come across the eastern and the leeward side, that is when we refer to those winds as Chinook. Okay. Then you have Mistral. Mistral is a cold local wind. It is in existence over the region of France, Spain, and the region of Europe, especially during the winter months, right? And they move over from land over to the area of Mediterranean. And the reason is very simple here also. Mediterranean in the winter, water body is comparatively warmer than the land area. The land area is very, very cold during the winter. Water body is comparatively warmer, isn't it? So here what you will observe is that when the land basically gets, so here the land gets very cold in this region, in this entire area the land will get very, very cold during the winter. So this will develop a high pressure. As it develops a high pressure, Mediterranean, which is comparatively warmer, will have a kind of a low pressure, right? So Mediterranean will have a kind of a low pressure. So that is when the movement takes place. And this is what is Mistral. So Mistral is a cold local wind which blows in Spain and France from northwest to southeast direction. These winds are more common and effective during the winter season because of development of high pressure over the Europe and low pressure over the region of Mediterranean. The arrival of Mistral causes sudden drop in air temperature to below the level of freezing point. Okay? Snow eater. Snow eater, Chinook is referred to as snow eater because it melts the snow. Why? Because it is warmer. Why is it warmer? Because it is coming down the slope. So, coming down the slope, how does it mean that it is warmer? Remember, yesterday we have had a discussion about adiabatic heating and adiabatic cooling, where we observed that as the wind cools down significantly, or it expands in volume, its temperature drops. As it contracts in volume or is getting compressed, its temperature increases. So when we talk about Chinook, as it comes down the mountains, it undergoes that level of compression. And that is why you experience the rise in temperature. Is that understood, Pooja? Chinook and Phone, they are same in terms of principle, but Phone is specific for Alps, Chinook is specific for Rockies. Yes, Satyanarayan, correct. Now we come across another local wind, that is blizzard. Now, blizzard is in existence in the region of North America, northern portion of Europe, northern portion of Siberia, and some areas of Asia. That is in those northern portions, polar areas in higher latitudes. That is where you have very cold polar winds which come in, and these cold winds, they are having a speed of roughly around 80 to 100 kilometer per hour. But when these winds come over, they manage to pick up the snow and ice. So in all those months, in those areas, especially in the higher latitudes, you will have a lot of snowfall, right? Now when the cold winds, they start blowing, they will pick up those snow particles. So the winds have a characteristic of very cold temperature, right? And they will have that whitish powdery dust like appearance because it is the snow that they are carrying, and they will lead to the sudden dip in temperature also. So that can be very devastating. So that is when it is always advisable to stay indoors. Otherwise, it can lead to proportion or devastation of significant proportions. So, blizzard is a violent, stormy, cold, and powdery polar wind. Powdery here because you have snow, lot of snow powder which is carried by the wind, laden with dry snow, and is prevalent in the north and south polar region, Siberia, Canada, and the USA. Now the visibility becomes remarkably low because of the snow and the ice crystals which are present. Okay, the velocity ranges between 80 to 96 kilometer per hour. Arrival of these winds causes sudden drop in air temperature to sub-freezing level. Thick sheets of snow gets deposited in the process. Now, ideally, in almost all these areas in the polar regions, these particular events such as blizzard, they will be impacting only the polar areas, only these polar areas. But in North America, it hits United States as well, especially the central portion of United States. Why? Because in United States, if you take a look at the mountain range, you have north to south mountain range on both sides, but you don't have any east to west mountain range barrier. Like in India, you have the Himalayas as the east to west mountain barrier, right? But in US, you don't have anything like that. So these winds, they come over and they will bring about a sudden dip in temperature. Okay, many people, they lose their life, especially the homeless. And regardless of whatever might the perception be in our minds, whatever might be the perception through the various TV channels, etc., the problem of homeless is very significantly large in United States. You have a large section of the homeless population. So there you have a lot of people who tend to lose their life on an annual basis because of these blizzard events. Okay? Yes, Pranay, that is correct. Which part of USA? Alaska? No, not Alaska, the central portion. It is this portion which gets hit. Okay, near the Great Lakes area. In that area, the Great Lakes, which forms the boundary between the region of Canada and US, that is the region which gets impacted. Nikhil, last year, and illegal immigrant Indian family lost their life. Yes. That is when the blizzard basically became very popular in our news channels as well. We had an illegal immigrant family from India, and you had a husband, wife, and their kid. They were crossing the Canadian border illegally, obviously trying to enter into US. And that is when they were stuck with blizzard, and they basically they all of them froze to death because it brings about almost the visibility is zero. So even if you raise an alarm for help, you won't get any visibility in that area. And in that wilderness, basically the temperature drops quite significantly. So that is one of the very famous migration route for Indians, right? We Indians, we have also started migrating quite significantly in large numbers. When we come to the portion of migration, we'll talk about in detail if time permits. But you have many of the Indians, especially in the northwestern part of India, they migrate. That is generally from Punjab, Haryana. You will find people migrating. First of all, they go to Greece or Cyprus. From there, they enter into Europe. From Europe, they try to move to Canada. In case they don't get an entry directly to Canada, from Europe they will enter into Canada, and from Canada they enter into US. And otherwise, they migrate into the region of Italy. So Italy is also suffering, and significantly, that has raised a lot of disharmonious public sentiment against the Indian migrant population in Italy, because there also you have a lot of illegal Indian migrants moving to Italy and working in their farmlands, right? And to add to the irony of it, if you actually investigate, there's a very beautiful documentary which has been made by the DW channel. If you watch that DW, it is present on YouTube. There's a very heart wrenching, to say the least, but it is a wonderful documentary which talks about the fact that how migrants from India, they they have land in India, right? In their land in India, they basically are calling the migrant laborers from Bihar, Odisha, UP to work in their land in Punjab, and then they themselves migrate to work as laborers in Italy. So that is a very strange aspect of Indian migration pattern which is unfolding in front of our eyes in the 21st century. Anyways, now coming to another local wind, and that is Sirocco. So Sirocco, this is a unique local wind which comes into existence or genesis from the northern portion of Africa. And from the northern portion of Africa, there, as the wind moves in the northern, so that is the region of Sahara Desert. In the Sahara, you have significant amount of red sand as well. Red sand is picked up by these winds, right? So let's suppose you have the Sahara, this is Africa, in between. After that, let's suppose you have the region of Mediterranean. Then let's suppose again you have the European region. So this wind originates from Africa, picks up the red sand particles, okay, lot of them. As this moves over the region of Mediterranean Sea, these red sand particles, they are encapsulated by a lot of water vapor which is picked over from the region of Mediterranean Sea. And then when they hit the Italian coastline, southern Italian coastline, they bring rainfall, but the rain droplets have red color because of the red sand that they carry. That is why in the southern Italian coastline, it is also known by the name of blood rain. Okay, so Sirocco is again a warm, dry, and dusty, full of sand local wind that blows in the northerly direction from the Saharan desert, and after crossing over the Mediterranean Sea, reaches the region of Italy, Spain, etc. It is in that area of Mediterranean Sea where it will pick up substantial amount of moisture. And after picking up moisture, it dumps it over the Italian coastline generally. While passing over the Mediterranean, it picks up moisture and yields rainfall in the southern part of Italy, where the arrival of rain is called blood rain. Okay, why? Because of the fallout of the red sands with the falling rains. So this is what Sirocco is known for. So these are your types or categories of local winds. I hope by now you are able to understand the larger trend, that these are in existence over a small part or a small region, and that too for a very small time duration. Okay, they are not in existence perpetually for a endless or a very long time duration. Okay, so this is the image of the rough image of these particular local winds, but I have provided you with a kind of a list. Use it only for your prelims, for your revision. Look at what is the nature of the wind, cold, warm, which region do they blow into. That should be more than sufficient. Okay, this is basically for your revision aspect. Okay, across all the various continents, we have covered this. Mistral Priya is basically the cold local wind which is in existence from the region of Europe, that is the southwestern part of Europe, into the region of the Mediterranean Sea. And in the winter months, the Mediterranean Sea is comparatively warmer, land area is very cold. So that is why you have a pressure gradient, local pressure gradient, which gets created, and they basically blow over. Right. Now, these are coming from the land areas or in the region of France and Spain. And in the winter months, they further lead to the dipping of temperature. When you have strong winds which blow, it leads to a fall or a significant fall in temperature thereby. Okay, that is Mistral. Right? Can a slight existence of blizzard be seen in Dras, Leh, Ladakh sector of India where the temperature? No. You have the cold winds which blow in that area, but blizzard is associated with when they are packed with a lot of snow, etc., and polar region. That is what the name blizzard is. Okay. So now we come to the portion of humidity and precipitation, where finally we will take a look at the cloud formation. Right? Many of you will uh, heave a sigh of relief after this, I'm sure. So this is where we will talk about the cloud formation. We'll talk about what is humidity. Humidity is not that very important for your examination, but for your prelims, you need to be aware that what do we mean by absolute humidity? What do we mean by specific humidity? What do we mean by relative humidity? So that basic you need to have. And then after that, we will talk about why condensation takes place. How is it that the condensation actually happens, how that process unfolds, what is dew formation. Then we will take a look at the aspect of the fog formation, different types of fog, different categorization of rainfall, cloudburst, hailstorm. Why is it that cloudburst events are very common in the mountainous areas? What is that hailstorm, which many of us mistake to be the kind of a snowfall? So these are the factors that we will cover in this. In the For the prelims here, almost all of them are important. For the prelims, that is types of humidity, the basics, okay? Then basically here also types of cloud, types of fog, thunder and lightning. These are your important areas. Cloudburst also, why does that happen? Types of rainfall. For the mains portion, cloudburst and hailstorms, types of rain, rainfall, and fog formation. These are the areas relevant for your prelims and the mains exam. That is something that we are going to cover. Okay. Before that, we need a break, or are we good to go? So we do one thing, we take a break. We take a 10 minutes break and we will be back. Okay. And then we will continue. So take a break. Okay. A confirmation about the audio, please, guys. If the audio is clear and available, kindly confirm. Thank you. Yes, an earthquake has occurred in Delhi. That is true. But then it is the tremors which have been felt. We don't know about the epicenter as of now. At least the news article that I was reading in that did not talk about the epicenter. So it is that Indian plate convergence and the collision of Indian plate with the Eurasian plate. That is what is leading to all these earthquakes in the northern portion. And it also tells you that it might be a kind of a forebearer of a larger earthquake which might emerge into the near future. So that can also happen. Coming back to the portion of climatology, we talk about humidity and precipitation. So, first of all, we talk about humidity. What do we understand by the term humidity? So, humidity refers to the amount of water vapor present in any parcel of air having a definite volume and temperature. Okay, the amount of water vapor in any parcel of air. So, when we say water vapor, here you have to understand that air particles basically in any portion of air that you consider, you will have gaseous particles as well. You will have the gases, that is nitrogen, carbon dioxide, oxygen, etc. You will have the dust particles, etc. So what is the amount of water vapor which is present? That is humidity. So if here you consider the two air parcels, obviously if you think about the second one, that is the one which represents greater humidity because the water vapor content is much higher. Now, humidity is basically in many of the times determined by the rate of evaporation, etc., which is happening in a region, but it is impacted severely by the temperature. Now, before we move on into the direct correlation between all of them, a basic understanding that when we talk about any air parcel, okay, whenever we talk about any air parcel as a point of reference, now here it will have various particles, water vapor particles, etc. Now here let's assume this has got the gaseous particles represented by the yellow dots. The yellow dots, let's assume, they end up representing these gaseous particles. Okay. Now, whatever is the spacing available in between, it is only there that the water vapor can be accommodated. It is only in these areas that water vapor basically can be accommodated in this region, isn't it? In these areas where we can accommodate the water vapor particles. Now, here, as you can see, there is no particular space for accommodation of any more water particles here, water vapor particles. And by the way, whenever we talk about humidity, many of the candidates, they get confused between water vapor and liquid water droplets, right? So water vapor is the gaseous state of water. Water vapor is not something that you will experience by the sense of touch. It is what you experience by the sense of touch, that is the liquid water droplet. So I hope that difference is understood. Now, coming back to this, here when we talk about this air parcel, this has got a limited capacity to accommodate the water vapor, gaseous particles, etc. In this case, clearly the air parcel doesn't have any capacity to accommodate any greater amount of water vapor. So that is referred to as the carrying capacity of the air parcel. So when we talk about carrying capacity, what does that refer to? Carrying capacity basically indicates the amount of water vapor that any air parcel can carry with it, can hold within itself at any given temperature. Okay, it cannot carry more than that. So, amount of vapor that an air parcel can hold. Okay, amount of vapor that an air parcel can hold at any given temperature. Now, if you vary the temperature, you and I, we cannot vary the temperature. Let's suppose due to heating or cooling, that temperature is altered or that temperature gets varied. Now, as the temperature changes, the carrying capacity also tends to change. Right. Carrying capacity, think about it in simplest of the terms. For example, let's suppose your parents send you to the market to bring vegetables, bag of vegetables. Now you will also have your carrying capacity. Beyond that, either your hand will break or your neck will snap open or your legs will snap. So you also have a carrying capacity. Similarly, the air parcel also has got a carrying capacity. It cannot hold water vapor beyond that. Now, this carrying capacity is dependent on the temperature, is and can be influenced by the temperature. How? So let's consider certain conditions. Let's consider the condition where we heat it up, where we heat this air parcel. Now, upon heating, what will happen? Particles will gain energy, isn't it? Many of these particles will escape the system. So, upon heating, what do you have? At least the gaseous particles, etc. Many of them can escape the system. The air becomes lighter. So upon heating, it will expand, the air will also expand. And here, as compared to earlier, you can see that now you can accommodate many more water vapor particles, isn't it? Because now you have lot more spacing between the gaseous particles which are present. So now you can accommodate many more particles of water vapor. Conversely, let's suppose we cool this down. We cool it down. So basically, in that scenario, what we confront, what we encounter is a smaller air parcel. And a smaller air parcel, meaning the earlier particles, they would have lost their energy, they would have stuck much closer to each other. Right? More particles might have entered into the system. Now, due to this, what is the actual outcome of it? So, due to this, now you can see that the space available for the water vapor is much lesser as compared to earlier. Water vapor will not have much greater space where it can accommodate itself, can it? So, the carrying capacity of the air has reduced. So, can we come to a conclusion where we say that the carrying capacity of the air parcel always increases when the air parcel receives heat, when the air gets heated up? Its carrying capacity improves. That means it can carry or it can have within itself much greater quantity of water vapor, which can be included. So here we can have our first set of inferences. Carrying capacity of air increases with heating. Right? And carrying capacity of air decreases due to cooling. Okay, so that is what you have, where the amount of vapor which is contained in any air parcel, now It is always dependent on carrying capacity. Now, any air parcel cannot include more vapor within itself as compared to what it can carry in complete in total, right? So that carrying capacity in itself is prone to change due to the impact of temperature. So water carrying capacity of an air parcel varies with the temperature of air. A warmer air parcel can hold more amount of vapor as compared to a colder air parcel. Okay, so whenever an air parcel is very hot or very warm, it will have much more capacity to include much more amount of vapor. Further, if it gets heated up, it will be able to hold much more amount of vapor furthermore. Now here we come across the different types of classification of humidity. Now humidity basically is measured on a day-to-day basis, on an hourly basis also. Now that is the amount of water vapor that you have to measure. So when you are measuring humidity in some way or the other, you are basically trying to find out what is the total amount of vapor which is contained in that, right? So how do you do that? Basically, you carry out that process, you carry out that exercise with the various different processes. So you can measure absolute humidity, you can measure specific humidity, or you can measure relative humidity. All of these are nothing but your measures of humidity. So what are they? Absolute humidity. So when we say absolute humidity, it basically measures the weight. It measures basically the weight or the mass of water vapor in 1 meter cube or any volume of air, right? So for example, if I take you back to this image, so let's assume the volume of this air parcel is 1 meter cube, or let me draw a new diagram altogether. So if let's assume I consider an air parcel of 1 meter cube, let's say the volume is 1 meter cube. Okay. Now here in that 1 meter cube, what is the presence of water vapor? What is the overall presence of water vapor? That weight is what gives us an idea about absolute humidity. So let's assume that the weight of the water vapor is 5 grams or 10 grams, suppose, right? So let's assume weight of vapor is 10 grams. So what will be the absolute humidity? Absolute humidity in this case will be 10 gram per 1 meter cube. So 10 gram per meter cube. Okay. So that is what you observe or experience in this situation. It is experienced in gram per meter cube. Now, absolute humidity is generally observed to be decreasing from the region of equator to the region of the poles. That is the general experience that you will have, that it decreases from the region of equator to the region of the poles. Why is it so? Because in the region of equator, it is warmer. So its capacity to hold vapor is much more in the region of equator, right? So chances are if the moisture is available, it will be able to hold that moisture. But as you move towards the region of the poles, the temperature becomes very, very cold in the process. And with colder temperatures, we do know that the moisture carrying capacity is very less. So that is why around the region of the poles, the moisture carrying capacity being less, it will never hold beyond that point, right? So it decreases from equator to the poles, again, based on the same principle that carrying capacity reduces with temperature. Reduces with a reduction in temperature. That is something that you experience in the case of absolute humidity. Then we have what is referred to as specific humidity. This is also a measure of humidity in itself. But specific humidity is different in the sense that in the case of absolute humidity, we were measuring the weight of water vapor per volume, 1 meter cube of air parcel. In the case of specific humidity, we are measuring the weight of vapor in 1 kg of air parcel. And when I say 1 kg of air parcel, we basically are referring to the weight or the mass of the the air molecules, the gaseous molecules, etc. That is how we end up measuring it. Okay, so here mass of water vapor per kilogram of air, that is your specific humidity. So that is what is much more representative in the sense that this doesn't change significantly with the change in volume, change in temperature, etc. Why? Because let's assume that you change the or you heat that air parcel, its volume will increase. But when we talk about 1 kg of air parcel, it will constitute of the same amount of gaseous molecules involved, right? So within that 1 kg, if you consider 1 kg in small volume or 1 kg in larger volume, what is the total amount of water vapor that is contained within them? So that is something where you observe that it is seldom affected by change in volume and temperature. So it is not going to have any unit because both water vapor as well as the mass of air, both of them, they are represented in terms of kilograms or grams. So they will cancel out each other. That is why specific humidity generally is not going to have any unit. Okay. In the earlier one, you had a unit of gram per meter cube. In the second case, you don't have any particular unit. It is unitless quantity. Now, then you have relative humidity. Now, this is the one which you confront, that you come across in your news channels. If you observe the weather reports in your newspapers, if you look at the weather reports, there also you find it mentioned. So that is the humidity which is talked about. So what is relative? Relative always is in comparison with something. Whenever we talk about relative humidity or relative anything, it is in comparison with something. So any air parcel at a temperature will have XYZ as the carrying capacity. Let's assume that it has a carrying capacity of 10 grams. Now, that is the total vapor that it can carry. But at any point of time, what is the vapor that it is carrying, the amount of vapor that it is carrying? That is relative humidity. So if we simplify it, let's suppose here we talk about relative humidity in the sense, let's suppose we have the air parcel. Now, temperature of, let's assume 35 degrees Celsius, carrying capacity, if I assume carrying capacity to be 10 grams, the vapor present, let's assume is 5 grams. So relative humidity will be how much? Will be the total amount of vapor present as compared to what it can hold. So it will be 5 by 10 into 100, right? How much will that come out to be? 50%. That is your relative humidity. Okay, that is what we understand as relative humidity. Now, here relative humidity also changes with the change in temperature. It changes significantly. Changes with the change in temperature. How? So, think about it. Suppose I consider or I give you a situation. I give you a situation or a scenario where you have an air parcel, and in this air parcel, let's assume this air parcel is at a temperature of 30 degrees Celsius. Okay. Here, let's assume the carrying capacity is, when we talk about at 30 degrees Celsius, the carrying capacity is 10 grams. vapor which is present, is, let's keep it 6 grams. So relative humidity in this case will be how much? Let me know. What will be the relative humidity in this case? 60%. Good. Okay. Now, if for some reason I were to heat it up, right? Let's suppose I heat this up. I heat this up in the sense that I take the temperature of this to take the temperature of it to, let's say, 40 degrees Celsius. Okay. Now 40 degrees Celsius, I have heated it up too. So carrying capacity will also increase, because with heating, we do know that the carrying capacity increases. So carrying capacity has increased to 12 grams, let's assume. Vapor present remains the same in the case if there is no further vapor which is added. So vapor present remains to be 6 gram as was the case earlier. The same amount of vapor is present. So vapor present is 6 grams again. So what is the relative humidity in this case? Good, 50%. Okay. So upon heating, what has happened? When I heated it up, or when basically the air heated, what happened? Its relative humidity reduced. Why? Or what does that indicate? That tells you that the air has got much more space to accommodate much more water vapor. Okay. Then, if let's suppose I cool it down, I provide cooling. And by the process of cooling, from 30 degrees Celsius, I have reduced the temperature, let's suppose, to 20 degrees Celsius. 20 degrees Celsius. Now the carrying capacity, let's assume, has become 8 grams. Vapor present is same, as is the case, because let's assume there is no net addition or removal of vapor from here. So vapor present is 6 grams. So what is the relative humidity in this case? Good. It is 75%. Right? I hope that is understood. So here what do you see? You will observe that because of the change in temperature, the relative humidity undergoes a change. Now, how does it impact us? It impacts us in the sense that if air cannot hold any more water vapor, then that is when you basically reach a level of saturation, that the air cannot hold any more of it. Now, we experience humidity in our day-to-day lives. When you go to, let's suppose, a desert area, or remove the desert, or forget it, think about if you are in northern plain region, especially in the region of Punjab, Haryana, Delhi, in those areas. Now, even if the temperature is very high, around 40, 42 degrees Celsius, you will not experience that kind of a, a very uncomfortable feeling, because wherever you will start sweating, you will sweat, you will perspire profusely. You will have a lot of perspiration. But all that perspiration will be lost into the air, into the atmosphere due to evaporation. Right? All that perspiration will be lost due to evaporation. And whenever that evaporation will happen, you will experience a cooling process. The body temperature will cool down. Right? On the other hand, if ever you happen to spend, let's suppose, especially during the rainy season, if you spend some time in Mumbai or any coastal area, Trivandrum or Chennai or Kolkata or Vishakhapatnam. In those areas, even if the temperature is 32, 35 degrees Celsius, you feel a lot of discomfort. Why? Because when you sweat or when you perspire, that doesn't evaporate. It keeps on sticking to your body surface. And that is when you keep on perspiring, the perspiration keeps on happening, you keep on sweating more and more. And that is when you start losing fluids from your body. That is when you are required to take in fluids much more often. Right. So, with temperature, with the factor of temperature, that aspect of humidity also undergoes a change. So, when you perspire a lot, especially in the coastal areas, and that sweat is not evaporating, means what? It means the air around you doesn't have the capacity to accommodate any more amount of moisture. Okay. That means the air around you is already filled with moisture. But if the air around you is dry, it can accommodate much more, as is observed in the case of the dry inland areas such as Delhi, Chandigarh, etc., Rajasthan, etc. Despite the high temperature, the air is dry because its carrying capacity is high. It can accommodate a lot more amount of moisture. So, wherever that sweating happens, it will evaporate, providing that cooling action. Okay. So, oftentimes when you experience heat strokes, I'm sure sometime or the other in your life you would have experienced that due to a lot of sweating, excessive sweating, you feel dizzy, maybe you might have fainted once or twice. Now, why does that happen? That happens because there is lack of cooling. And when is it that you start feeling better? When you sit under a fan. Why? Because when the fan rotates, when the fan moves, or let's suppose the air conditioner, when it moves, the air is disturbed around you. So that means the air has got new capacity or fresher capacity to absorb more moisture. So that is when the sweat starts evaporating and you feel cooler, you feel better. So that is where humidity has got a direct role to play in our day to day lives. And we do know that relative humidity, or the various out of the various different types of humidity that you have, relative humidity is the one which is most widely used. So, a very quick revision of the different types of humidity that we have covered. So, we have covered the measurement of humidity in three parameters or three methods. In one method, we measure that in one volume, unit volume, 1 meter cube of air, what is the amount of moisture which is present? That is absolute humidity. In another one, we measure that in 1 kg of air parcel, what is the amount of water vapor that is present? That is specific humidity. But the most relevant one, which is used quite significantly and frequently, is the one where we measure that what is the carrying capacity of that air parcel, and as compared to the carrying capacity, what is the amount of moisture that the air is carrying. That gives us relative humidity. Okay. Issue of not absorption of sweat was faced in Delhi NCR after sudden rain. So, Gaurav, in the rainy season, everywhere you will experience this. Why? Because in the rainy season, the air has got a lot of moisture. Air has around you will have lot of vapor. So, in rainy season, you will experience this. But in the coastal areas, you will experience it all throughout the year. Right. That is why in the coastal areas you will experience that despite the fact that it is evening, night, etc., you continue to sweat. It doesn't stop. So that is a feature, that is a phenomena associated with the regions where you have lot of moisture. Okay. I hope that is understood. Let me write this conclusion in a separate slide so that it becomes easier for you guys. So, variation of relative humidity with temperature. Variation of relative humidity with temperature. So we do know that due to heating, the carrying capacity increases. And relative humidity is what? Relative humidity is vapor present by carrying capacity capacity into 100. So if that carrying capacity is altered, that means you will have a variation in relative humidity. So with a rise in temperature, with an increase in temperature, carrying capacity increases, and as the carrying capacity increases, what will happen to the relative humidity? Relative humidity reduces. Right? With cooling, whenever cooling is experienced, carrying capacity reduces, relative humidity increases. Okay? I hope we are comfortable up till this point. Relative humidity, is it understood? Any doubts that we have? Please let me know. Priya, have you understood that specific humidity? You had asked a question about specific. I hope that is also understood about specific humidity. Okay. So now we talk about, or we basically try to extrapolate this concept. We try to build up on this particular concept. Let us try to understand how the implication of it. So always when you try to break this down, or when you try to understand these phenomena, always advisable, do it with the help of these molecules, drawing of molecules, particles. It becomes easier for understanding as well. So here, let's assume you have an air parcel at a temperature of 30 degrees. Okay. Carrying capacity is 8 grams. Vapor present already in this. The vapor present is already 6 grams. Okay. Now, if suppose I heat it up further, or we'll come to heating later. Let's suppose I cool it down. And I bring the temperature by cooling. I bring the temperature to, let's assume, 20 degrees Celsius. So much so that the carrying capacity is 6 grams. Vapor present is also 6 grams. What will be the relative humidity in this case? In this situation? 100%? Simple? Clear? Relative humidity will easily be 100% in this, isn't it? Relative humidity in this case is 100%. Earlier, relative humidity was 75%, as we found out earlier. Now it has increased to 100%. So by cooling, relative humidity has increased. But when we analyze this at 20 degrees Celsius, now there you will observe what? That basically you have the condition, you have the situation where now the air is having as much amount of vapor as it can carry. Right, the carrying capacity is already at 6 grams, and the vapor present is already also 6 grams. So now the air has got exactly as much amount of vapor as it can carry. It cannot carry any more. It cannot accommodate any more amount of vapor in it. So this is the condition where we say that the air has become saturated. It cannot accommodate any more amount of vapor. So that is why we say that the air has actually become saturated. So this is when we say air has become saturated. Okay, we can say that the air has become saturated in this case. Now from here we can carry out certain exercises in the sense that we can heat it up again now, or we can cool it down further. So let us take a look at both of these situations. Let's assume that we cool it down further. Okay, let's assume that we cool it down. When we cool it down here, basically, now let's suppose after cooling it down, its temperature I have brought to 10 degrees Celsius, or by coming in contact with the colder ground surface, etc., its temperature has dropped to 10 degrees Celsius. Carrying capacity has reduced to 4 grams. Carrying capacity has reduced to 4 grams. Okay. And the vapor which is present here, the vapor which was earlier 6 grams, now can that vapor be accommodated in the air parcel? What do you think? Because the carrying capacity in itself has been reduced only to 4 grams. So can this air parcel accommodate any more amount of vapor? Absolutely no. It can accommodate only those 4 grams. So what will happen to those extra 2 grams? You will have 4 grams will be carried over, 4 grams will be present, vapor will be 4 grams. What about the extra 2 grams? Very good, Himadri. Pranay, good. So these extra 2 grams that you have, they will condense. The air will not be able to hold them at all. This extra 2 grams, they will get converted into liquid water droplets. They will get converted into, or they will basically condense from vapor state into liquid water droplets. So this extra 2 grams undergoes condensation. Condensation. Okay. This is what undergoes condensation, right? So when you cool the air beyond the point of saturation, what is that point of saturation? Point of saturation is when the air is holding within itself as much amount of vapor that it can carry. That is the point of saturation. That temperature at which this state is attained, that the air is having the carrying capacity and the vapor present is the same, that is what is referred to as the saturation temperature. If you cool this air parcel beyond that point of saturation, the extra droplets which it cannot, or the extra vapor that it cannot hold anymore, all those extra vapor, they will start to condense. And that is when you have the liquid water droplets which are associated. Okay. On the other hand, if I were to heat it from this stage, right? Let's suppose I would have heated this air parcel from 20 degrees Celsius, I would have taken it to 22 degrees Celsius. Carrying capacity would have increased. Carrying capacity would have increased, let's suppose, to 7 gram, right? Vapor present would remain the same as 6 gram. It would have become unsaturated now. Okay, it would have become kind of unsaturated. So the relative humidity in this case would have become how much? It would have become roughly around 85%. What is the relative humidity in this case? Yes, 85% roughly. Okay, so from the point of saturation, when the air becomes saturated, if you heat it up, it becomes unsaturated again. Its relative humidity reduces, in the sense now it can hold up more moisture. But if you cool it down at that point itself, that is when it will undergo condensation and you will have the presence of condensates or liquid droplets. Okay? Is this clear? Good. Is the same condition when we normally say at home that no leaves of tree is blowing, no air is in the, it cannot be the case that no air is in the environment, if unless and until it is again one of those developed English that you are using. Because when you say that there is no air in the environment, how are we breathing? Right? It is what we are breathing is air. When you see that there is no movement of leaves, etc., there is no wind, right? There is no wind motion that is there. When there is wind, then generally saturation is not reached easily, because whatever water vapor would be present, wind would carry it away with itself. Okay. The preferable humidity level should be roughly around 40%. 40% is 40 to 45% is good. Okay, because see, in Bangalore, that is why I had attached this image as well. In Bangalore, sometimes what happens, if this is around 40, 50%, 55% comfortable. In Bangalore, in the month of February and March, generally every year this happens, that the humidity level, relative humidity level reduces to the extent of around 30, 34%, sometimes even 20, 25%. Now, in that situation, what happens? You would have read it in news articles, or those of you belonging from the region of Bangalore, you would have experienced it personally. That when you touch something, you get a lot of static shock, right? Because the air around you is so dry that the rubbing of the air develops charge. So when you touch, let's suppose when you're sitting in a place, you touch someone, you will get some static shock. You'll touch a metal object, you'll get some static shock. So that is something which happens when the condition is very dry. The skin starts rupturing, and the impact on human health is also adversarial when the humidity level is very low. Okay, I hope that is understood. Now, after this, we come to the portion of saturation of air. But before that, we take the long break, the snacks break in general. Or can we continue for some time now? We had just taken a break. Can we continue for further 10, 12 minutes and then we take a break? Yes? Okay. So we have a consensus. Good. So now we come to the portion of saturation of air. When relative humidity more, it requires less cooling to reach saturation. Yes. So here we come to the portion of saturation of air. What is saturation? Saturation is when something doesn't have a capacity to hold anything at extra or additional within it. When that capacity is completely fulfilled. So when you have the air parcel having the no capacity to hold any more amount of water vapor, when the vapor present is equal to the carrying capacity of that air, we say that the air is saturated. So at the level, so air containing moisture to its full capacity at any given temperature is said to be saturated. Okay, so here in this condition, relative humidity will be how much? Will be, when the air is saturated, the relative humidity is good, 100%. Okay, that is the condition of relative humidity. The temperature at which this saturation is attained, that is referred to as the saturation temperature. Temperature at which saturation is attained is the saturation temperature. Okay. Now, furthermore, here, how do we attain or how do we observe that the air has attained saturation? basically when the air experiences cooling, right? It might happen that the relative humidity is 85% or 60%. It experiences cooling, and then eventually it will, by cooling, it can reach saturation. Now, here, if we consider an area across the coastline, for example, let's suppose, now Mumbai, Goa, Trivandrum, Kochi, any of these. Now, there, if you cool it down, the air, already the humidity level is very high. So, let us consider these cases. Let us consider the situation in Mumbai, and also let us consider the situation in Delhi. Delhi, why? Because it is a dry region in terms of the air moisture presence. It is a dry region, and generally the humidity level is very low. So in Mumbai, temperature of 35 degrees Celsius, relative humidity, let's assume, is 80%. Okay. In Delhi, temperature of 35 degrees Celsius, relative humidity of 40%. Now, if I were to cool this down upon cooling, what were to happen? What will happen in this case? If I cool it down, basically, relative humidity will increase. So let's suppose it has come to 30 degrees Celsius. Relative humidity has increased to 100%. Or let's not go for directly 100%. Let's go for 95%. Let's say we cool it down again. Again, in this situation, let's assume I have brought the temperature to 25 degrees Celsius. Relative humidity has now become 100%. Now, if I were to cool this down furthermore, remember from the previous slide, if I were to cool this down furthermore, if there is further cooling, even by 1 degree, okay, if I bring the temperature to 22 degrees Celsius, I have cooled it down. So, relative humidity will continue to remain 100%. But what will happen in this case? You will experience condensation. This is the point where the air has hit saturation. The air has hit saturation at 25 degrees Celsius. So if I cool it down further, there will be condensation around. How will condensation happen? In the air around us, how will condensation happen? Will we start observing raindrops forming in front of our eyes? No. So sometimes during the rainy nights, that is when it is the rainy season, in the night time when the temperature drops, you would have observed that small droplets, they basically form on any of the surface, metallic surface, etc. During winter nights, you observe the dew formation, right? So that is how condensation happens. So this is where condensation, yes, Parshuram, condensation occurs. Okay. So when you cool it beyond that point of saturation, what will happen to the excess vapor? It will try to find any surface which is there, anywhere, any place, any surface. It will start. So, even for example, those of you, at least I can tell it because I have specs. So, those of you who are also having specs, you will observe that droplets will develop even on the glasses of your specs when suddenly that condensation takes place, right? So, that is condensation observed in the form of dew, observed in the form of various other factors. But let us take a look at some other condition. Let us talk about, or let's do one thing. Let's not talk about Delhi. Let's talk about Leh. Okay. And let's talk about the condition of relative humidity to be here 20%. Because Leh Ladakh is very dry, very dry condition, isn't it? So here, if I cool it down, let's say substantially from 35 degrees Celsius, I have cooled it down directly to 20 degrees Celsius. Relative humidity in this duration from 20% has improved to, let's say, 85% or 80%. I cool it down further. I bring it to 5 degrees Celsius. And when I cool it to 5 degrees Celsius, let us assume that the relative humidity in this case has reached around 95%. Okay, that is what the relative humidity has reached to. Now here, when I further want to basically, or in that region, let's suppose in Leh Ladakh, further cooling happens. So let's suppose further that has been cooled down to 0 degrees Celsius. Okay, 0 degrees Celsius is when the relative humidity in this case reaches 100%. This is the point of saturation, isn't it? Let's suppose that during the night time is when we will observe the formation of or the reduction in temperature, and night time is when we observe this saturation. Now, in this case, if I reduce the temperature furthermore by 1 degree, 2 degrees Celsius, here, I further reduce the temperature to minus 2 degrees Celsius. Now what will happen? Again, in this case, now vapor will not get converted into liquid droplets. This time, vapor will get solidified into ice particles and ice crystals. This is when you observe on the ground, especially those of you living from the or belonging to the mountainous areas, or even in the region of Punjab plains, and also the region of Himachal, Uttarakhand, all the mountainous areas, you would observe early in the morning that across these metal poles, the electricity poles, etc., you have very thin sheet of ice, transparent, obviously very transparent, thin sheet of ice which builds up. That is your condensate. It has developed there, it has built up there due to the process of condensation. So here also, basically, in a way, crystallization occurs or condensation occurs where ice is created. Here you have liquid water droplets in the earlier case. Liquid water droplets, mostly dew, is what gets created. Whereas in this case, you will have ice or frost formation. Frost is basically when on the ground surface you'll find very thin sheet like formation of ice, which you can hold it up and you can wave it up off as well. That is something which is very common in those areas, especially those of you from the eastern part, that is from the region of Arunachal, from the region of Sikkim, even North Bengal, from the region of Uttarakhand, Himachal, Jammu Kashmir, and also Punjab. In those areas you experience this. That is where you have these thin sheets of ice which get created, which get formed. And on the ground surface, on the metal sheets, if you have parked your car outside or your scooter outside, on the scooter metals also, this will develop. That is what is frost. So in all this, what do you observe? That condensation will always occur when there is cooling beyond the point of saturation. If that point of saturation is above 0 degrees Celsius, that is above freezing point, you will have liquid water droplets in the dew formation, etc. If that point of saturation is below the freezing point, you will have ice formation, right? This is not rainfall, by the way. This is still, now we have not talked about rainfall or cloud formation. This is purely condensation happening at the ground surface, air around us. Now, this is the reason why you will experience, and listen to this carefully, in the coastal areas, you will experience the dew formation happening almost on a daily basis. In the afternoons, in the evenings, you'll find in the coastal areas almost on a daily basis that there will be dew formation. Whereas in the inland areas, because the humidity level is so very low, that nighttime temperature of 25, 26 degrees Celsius is not enough for dew formation. That is why in the interior areas, dew formation would be observed only during the winter nights. But in the coastal areas, almost on a daily basis, because relative humidity is so very high that even cooling up till here, observe, in Mumbai, saturation has been reached at 25 degrees Celsius itself. But for that saturation to be attained in Leh or Ladakh, it will have to reduce the temperature to 0 degrees Celsius. Same is the case with Delhi as well. So that is why coastal areas experience dew formation on a daily basis, almost in the evening, right? Whereas the interior areas, they experience only during the winter when the temperature dips so significantly. Understood? Is that understood? Hailstones will come to it. Means this way, uh, water vapor can be seen on sugarcane leaves in field during early winter morning. Yes, that is also your dew. In which condition hailstones will cover as we move ahead. Okay. So that brings us to the entire concept of condensation. And even though we have already covered it by the basics that we have seen right now, so condensation, something that you and I we experience on a day-to-day basis, right? When you take a bottle out of the refrigerator, you keep it out in the open, any bottle, water bottle, or your soda bottle, cold drink bottle, Coca-Cola, Pepsi, anything that even you buy from the market, and all of you would have experienced this. When you keep it on the table for some time, you will observe liquid water droplets developing on the outside, right? If you keep it on the table, liquid water droplets will develop. Now that is condensation. Condensation of what? Condensation from the surrounding air. Okay. So, for example, leave alone water bottle. Even if you take any metal utensil, generally that you keep in your refrigerator, etc., you keep it on the table. There also, if you keep it for some time, you will observe some small droplets develop on the outside of that utensil. That is condensation. Okay, so this is something that I'm sure you might not have noticed it, but you would have observed it, I'm sure. So if you have basically a bottle, okay, let's assume you have that irregular shaped bottle. Okay, now after some time, you will observe that small droplets they build up on the sides of the bottle. Now, why does this happen? So let us understand that. So basically, the bottle which is kept in the refrigerator, let's suppose it is kept at 1 degree Celsius or 2 degrees Celsius. Okay, the bottle. So the surface of the bottle is, temperature is 1 degree Celsius. Now, the air around you might have a temperature of 25, 30 degrees Celsius. It is in refrigerator that it is cold, but the air around you might be at 25, 30, 35 degrees Celsius. So let us assume that the air around this bottle is particularly, the air around this particular bottle, let us assume, it is at a temperature of 30 degrees Celsius. Now this air, when it is getting in contact with the bottle, the air also is cooling down substantially at a very fast rate. The air is cooling down, isn't it? So the air, because of getting in contact, air cools down very quickly as it is in contact with the bottle. So what will happen? Air will hit saturation point. Further, if it is cooled down beyond that, it will undergo condensation, isn't it? So here, it basically reaches saturation, cooled beyond that, and then condensation in the form of tiny droplets. But understand, whenever condensation has to happen, whenever, it cannot happen into thin air. Condensation will always happen when there is a surface in contact. Only in that situation will the condensation happen. So you will observe the condensation to happen either on the surface, that is the ground surface, or your vehicles that you have parked outside, or the bottles that you keep on the table. So condensation will always require a surface. Condensation can never happen into thin air. Okay, that is the basis of cloud formation, fog formation. Everything is dependent on that. Now, one form of condensation that we experience on the ground surface is what is regarded as dew, right? So that dew, basically, these are tiny drops of water that form on cool surfaces at night when atmospheric vapor condenses. The dew point is the temperature the air needs to be cooled to in order to achieve a relative humidity of 100%. Only when the relative humidity is 100%, that is only when the air is saturated. Only cooling beyond that will lead to occurrence of dew, isn't it? Cooling before that so will lead to the relative humidity reaching 100% or the air gaining saturation. Only if you continue to cool it further down will you experience that dew formation or that accumulation of droplets. So here the dew, basically air cools down to reach saturation, cools beyond, that, leads to what? Dew formation. Because dew is a kind of a condensate. Okay, dew is nothing but a kind of condensation which takes place, nothing else. So dew point temperature tells you, or is that temperature, dew point is that particular temperature where the air will attain that saturation, the saturation point that we talked about. So it is that temperature at which the air reaches saturation. Beyond that, if you cool it down, dew will be observed. That is where, if the relative humidity of a region is already very high, such as Mumbai, Kolkata, Vishakhapatnam, Chennai, Goa, Trivandrum, Kochi, all the coastal areas you consider, generally the humidity level is very high. There, even slightest amount of cooling can take that saturation limit or can take the air to the saturation point, and immediately dew formation will be observed. Hence, in coastal areas, dew formation is observed almost on a regular basis. In coastal areas, In coastal regions, relative humidity is already very high. So, dew formation is observed almost every evening. Why evening? Because evening and night is when the temperature starts dropping. That is when you experience dew formation very, very frequently. Whereas in the inland areas, that is the regions such as Delhi, Chandigarh, etc., you will observe dew formation only during the winter months because the air generally is drier. Relative humidity is around the region of 30%, 40%. So it takes a lot of time or a lot of cooling for that relative humidity to hit the saturation point, and then furthermore cooling to bring about condensation. Okay, right? Okay. So we take a break, and we after this we continue the remaining portion of cloud formation, etc. So your queries also we will resolve. So few of the queries will resolve quickly. What you said, that condensation only happens when in contact with ground? No, when in contact with a surface. A surface needs to be in contact. For cloud formation, dust particles play the role. And Gorapalli, we saw so much of dew and fog in winter season only. That is when the temperature reduces quite drastically so that the saturation point is reached. But in the case of the coastal area, you will observe this happening very frequently, not always in the winter season. Okay. Best example is cricket matches. So we take a break, guys, and we come back again at 6:05 when we begin the discussion again. Okay, take a break till 6:05. We continue.